In the darkness of space, something breathes. A silent colossus, hidden in the cosmic deep. Meet UY Scuti, the star so massive it could swallow our entire solar system and still be hungry. If the sun were a basketball, UY Scuti would be a stadium. Its surface would stretch past Jupiter, engulfing every planet we know. Discovered in the 19th century, this red supergiant stunned astronomers. They thought they knew big. They didn't. With a diameter over 1,700 times that of the Sun, it's a reminder that the universe plays on a scale we can barely imagine. Yet, despite its size, UY Scuti is dying. Burning through fuel at a furious rate, it will one day collapse and explode, a final breath, echoing across galaxies. How many more giants like this lie hidden, watching, waiting, vast beyond reason? UY Scuti stands as a testament to the awe-inspiring scale of the cosmos, captivating astronomers and enthusiasts alike with its extraordinary dimensions. This luminous red supergiant resides in the constellation Scutum, approximately 9,500 light-years from Earth. Its discovery traces back to the late 20th century during a period of rapid advancements in infrared astronomy. Initially catalogued as a variable star due to its fluctuating brightness, UY Scuti's true nature as a supergiant was revealed through detailed spectroscopic and photometric observations. By analyzing the star's light and temperature, astronomers deduced its colossal size, placing it among the most massive and expansive stars known. The journey to understanding UY Scuti's enormity involved meticulous measurements and sophisticated imaging techniques. Infrared surveys, such as those conducted by the Infrared Astronomical Satellite, helped penetrate the dense cosmic dust surrounding the star, revealing its true extent. Combining this with high-resolution interferometry allowed scientists to estimate its radius with increasing precision. These efforts confirmed that UY Scuti's diameter could stretch over 2,000 times that of our Sun, a staggering figure that underscores its status as a supergiant of unparalleled proportions. What makes UY Scuti especially remarkable isn't solely its size but also its brightness and the implications for stellar evolution. Its immense volume means it has a vast, tenuous atmosphere, which contributes to its variable luminosity and complex behavior. The star's discovery and ongoing observations continue to challenge our understanding of the upper limits of stellar size and lifespan. As astronomers refine their techniques, UY Scuti remains a focal point for studying the final stages of massive star development. Building on this understanding of its discovery, it's natural to wonder how UY Scuti compares to other famous giants like Betelgeuse and Antares. These stars, while impressive, are dwarfed by the sheer scale of UY Scuti, prompting curiosity about their relative sizes and brightness in the vast tapestry of the universe. When contrasting UY Scuti with other renowned red supergiants, such as Betelgeuse and Antares, the sheer scale and luminosity of UY Scuti becomes strikingly apparent. While Betelgeuse, famously positioned as Orion's shoulder, has long captured public imagination, it is dwarfed by UY Scuti's enormous dimensions. Betelgeuse's radius is approximately 700 times that of our Sun, translating to a diameter around 1.2 billion kilometers. In comparison, UY Scuti's radius is estimated to be about 1/700 times solar, equating to a staggering diameter nearly 3.4 billion kilometers, large enough to encompass the orbit of Jupiter several times over. Brightness, however, adds another layer to this cosmic comparison. Betelgeuse is a relatively bright star, with an apparent magnitude fluctuating around 0.5, making it easily visible to the naked eye from Earth. UY Scuti, on the other hand, is considerably dimmer in the sky, with an apparent magnitude around 8.5, rendering it invisible to the naked eye and requiring telescopic observation. Despite its lower apparent brightness, its intrinsic luminosity is extraordinary. UY Scuti's luminosity is estimated to be about 340,000 times that of the Sun, surpassing Betelgeuse's luminosity by a significant margin, which is roughly 100,000 times solar. Antares, another prominent red supergiant, falls somewhere in between, with a luminosity approximately 70,000 times solar and a radius roughly 700 times that of the Sun. These comparisons highlight that UY Scuti's size and brightness place it far beyond the typical red supergiant benchmark. Its colossal volume rivals the largest known stars, and its intense luminosity underscores its advanced evolutionary stage. While Betelgeuse's variability and proximity have made it a focal point for scientific study, UY Scuti's scale challenges our understanding of stellar physics. Its immense size not only dwarfs other giants, but also prompts questions about the limits of stellar evolution and the fate of such colossal stars. As we explore these celestial titans, it becomes clear that UY Scuti occupies a unique and astounding position among the universe's most extraordinary stars. UY Scuti's defining features as a red supergiant extend beyond its colossal size, embodying a combination of characteristics that highlight its advanced evolutionary stage. Its deep red hue signals a surface temperature considerably cooler than that of smaller, more compact stars, around 3,300 Kelvin. This relatively low temperature results in the star's distinctive coloration, which is characteristic of red supergiants. Its extensive outer layers are composed of cooler, diffuse gases, giving UY Scuti a sprawling, luminous envelope that can stretch hundreds of times the Sun's diameter. One of the most striking aspects of UY Scuti is its immense luminosity, which dwarfs that of our Sun by tens of thousands of times. Despite its cooler temperature, the sheer surface area of the star compensates, producing a radiant glow so intense that it can be observed across vast interstellar distances. This luminosity is a direct consequence of its expanded size. The larger the star, the more energy it radiates. Yet, despite this brilliance, UY Scuti's surface gravity remains extremely weak due to its enormous volume, making its outer layers loosely held and prone to pulsations and stellar winds. These pulsations are a hallmark of red supergiants, causing variations in brightness and size over time. The star's mass, estimated to be around 20 times that of the Sun, sits in an intriguing balance. While its mass is substantial, the distribution of that mass over an expansive volume results in a lower density compared to smaller stars. This low density allows UY Scuti's outer layers to be tenuous and extended, contributing further to its enormous apparent size. Its large radius, combined with the star's evolved state in the late stages of stellar life, signifies that UY Scuti is nearing the end of its life cycle, likely destined to explode as a supernova in the distant future. Understanding the key characteristics of UY Scuti not only emphasizes its grandeur, but also provides insight into the complex processes governing the evolution of massive stars. As we probe these attributes, it naturally leads to the question of how astronomers determine the true scale and distance of such an extraordinary object, a challenge that has driven the development of sophisticated observational techniques. Measuring the size and distance of UY Scuti presents formidable challenges due to its extraordinary brightness and vast size. Astronomers employ a combination of indirect methods and advanced observational techniques to unveil its dimensions with increasing precision. Central to this endeavor is the use of stellar parallax, a method that involves observing slight shifts in the star's apparent position against more distant background stars as Earth orbits the Sun. Although parallax measurements are highly effective for stars within relatively close ranges, UY Scuti's immense distance, likely thousands of light-years away, limits the accuracy of this technique alone. To circumvent this, astronomers turn to spectroscopic analysis, which provides vital clues about the star's intrinsic luminosity and temperature. By studying the star's spectrum, scientists determine its spectral type and effective temperature, which are essential parameters for estimating its luminosity through models of stellar atmospheres. Once the star's luminosity is known, astronomers combine this information with observed brightness, apparent magnitude, to derive its distance via the inverse square law of light. This approach, known as spectroscopic parallax, allows for more reliable estimates when direct parallax data are insufficient. Another critical tool in measuring UY Scuti's size involves interferometry, particularly optical interferometry, which combines light collected by multiple telescopes to simulate a much larger aperture. This technique can resolve the star's disk directly, providing a measurement of its angular diameter. When paired with the star's estimated distance, the angular diameter translates into a physical radius. This method has yielded some of the most precise measurements of UY Scuti's colossal size, revealing it to be hundreds of times larger than our Sun. Infrared observations also play a significant role. They penetrate the dense layers of gas and dust surrounding such luminous giants, offering clearer insights into their structure and temperature distribution. The combination of these techniques, spectroscopy, interferometry, and infrared imaging, provides a comprehensive picture of UY Scuti's dimensions and placement in space, enabling astronomers to refine their models of such supergiants and better understand the upper limits of stellar size. UY Scuti's prominence in stellar astronomy stems from its extraordinary size and luminosity, which push the boundaries of our understanding of stellar physics. As the largest known star, its sheer scale challenges existing models of stellar formation and evolution. Studying objects of such immense proportions offers crucial insights into the life cycles of massive stars, including their birth, growth, and eventual demise. UY Scuti's brightness and size also serve as a benchmark for refining techniques used to measure other distant celestial bodies, helping astronomers develop more accurate methods of distance estimation and size calculation across the universe. The star's unique characteristics provide a natural laboratory for testing theories about the limits of stellar stability. Its proximity to the upper bounds of known stellar dimensions raises questions about the physical processes that sustain such enormous structures without collapsing under their own gravity. Understanding how UY Scuti maintains its stability, or how it might eventually shed its outer layers, informs broader astrophysical concepts, including mass loss mechanisms and the role of radiation pressure in massive stars. Furthermore, UY Scuti's variability, its fluctuations in brightness over time, offers a window into the dynamic processes occurring within supergiant stars. Tracking these changes helps scientists decipher the internal mechanisms driving such variations, shedding light on the complex interplay between nuclear fusion, convection, and stellar winds in stars at the extreme end of the size spectrum. Studying UY Scuti also has implications for understanding the end stages of stellar evolution. As a potential progenitor of supernovae or black holes, its physical parameters help refine models predicting these cataclysmic events. By examining such colossal stars, astronomers gain perspective on the cosmic life cycle, from star formation to explosive death. Despite its significance, UY Scuti's enormous distance from Earth and its vast size make it a challenging object for detailed observation. The star's faint apparent brightness, due in part to its distance, complicates precise measurements, necessitating sophisticated instruments and techniques. This leads naturally into the next question. What obstacles do scientists encounter when trying to observe and analyze these distant colossal stars? Observing and analyzing a star as distant and colossal as UY Scuti presents an array of formidable challenges that test the limits of modern astronomy. Its immense size and distance, estimated to be over 9,500 light-years away, mean that even the most advanced telescopes receive only faint, diffuse signals, complicating efforts to extract detailed data. The star's brightness variations and extended atmosphere further obscure precise measurements, as the outer layers are often semi-transparent and fluctuate over time. These fluctuations introduce uncertainties in determining fundamental parameters such as size, temperature, and luminosity, requiring astronomers to disentangle intrinsic stellar behavior from observational noise. One significant hurdle lies in resolving the star's structure. with sufficient detail. Given its enormous radius, UY Scuti's apparent size from Earth is minuscule, rendering direct imaging a daunting task. Conventional telescopes cannot resolve the star's surface features, forcing scientists to rely on indirect techniques like stellar interferometry. While interferometry combines signals from multiple telescopes to simulate a much larger aperture, it demands impeccable calibration and synchronization, especially when observing such faint and distant objects. Even then, atmospheric disturbances can distort the incoming light, necessitating complex correction algorithms and adaptive optics systems. Another challenge stems from the star's variability. As a red supergiant, UY Scuti exhibits pulsations and mass loss episodes that alter its brightness and size over time. Capturing these dynamic processes requires long-term monitoring with consistent, high-precision instruments. Variations complicate efforts to establish baseline properties, making it difficult to create definitive models of its structure and evolution. Additionally, the star's extended atmosphere contains complex layers of gas and dust, which absorb and scatter light unevenly, adding further ambiguity to spectroscopic and photometric analyses. Despite these obstacles, advancements in technology have gradually peeled back layers of uncertainty. The development of more sensitive detectors, improved interferometric techniques, and space-based observatories has opened new windows into such stellar giants. These innovations have allowed astronomers to refine measurements and better comprehend the nature of stars like UY Scuti, setting the stage for an even more detailed understanding driven by ongoing technological progress. Advancements in technology over recent decades have profoundly reshaped our understanding of UY Scuti, transforming it from a distant point of light into a detailed cosmic phenomenon. Early observations relied heavily on optical telescopes, which, while groundbreaking at the time, provided limited insights into the star's true nature. The advent of infrared astronomy marked a pivotal shift, allowing astronomers to peer through dense layers of dust that often obscure supergiants. Infrared observations revealed that UY Scuti's size and brightness vary over time, emphasizing the star's dynamic behavior rather than a static, unchanging object. The development of more sophisticated instruments, such as adaptive optics and interferometry, further refined measurements of UY Scuti's immense radius. Interferometric techniques, in particular, enabled astronomers to resolve the star's disk directly, reducing uncertainties that had previously plagued size estimates. These technological strides confirmed that UY Scuti's volume surpasses earlier conservative estimates, though still within a range that challenges even modern calculations. Additionally, spectroscopic advancements have provided insight into the star's surface temperature, composition, and stellar winds, painting a more comprehensive picture of its complex outer layers. Parallel to observational progress, computational modeling has become instrumental. High-powered simulations now allow scientists to analyze how massive stars like UY Scuti evolve, pulsate, and shed material. These models incorporate detailed physics, such as radiation pressure and convection, helping to interpret observational data more accurately. Over time, this synergy between cutting-edge observation and simulation has clarified that UY Scuti's size is not a fixed attribute, but a variable that can fluctuate with its pulsations and internal processes. As technology continues to advance, our perception of supergiants like UY Scuti will only deepen. Each breakthrough narrows uncertainties, revealing not only the star's true scale, but also its role within the broader context of stellar evolution. These ongoing developments demonstrate that our understanding remains a work in progress, continually refined with every new instrument and insight. This evolution underscores the importance of technological progress in unlocking the universe's most enigmatic giants. Despite its awe-inspiring stature, UY Scuti is often the subject of several misconceptions that can distort our understanding of supergiant stars. One common misunderstanding is that UY Scuti's size is fixed. In reality, the star's outer layers are not static. They fluctuate due to pulsations and stellar activity, causing its apparent radius to vary over time. This variability underscores the challenge of pinpointing an exact size, as measurements are often averages rather than absolute figures. Another misconception involves the star's brightness. Many assume that being a supergiant automatically equates to immense luminosity, but this isn't always the case. UY Scuti's brightness is influenced by its vast size, yet its surface temperature, relatively cooler than smaller, hotter stars, limits its total luminosity. Consequently, some might mistakenly believe it shines brighter than it does, not recognizing the complex interplay between size and temperature in determining stellar brightness. There is also a tendency to conflate supergiants with the brightest stars in the sky. While supergiants like UY Scuti are enormous, they are not necessarily the most luminous or easily visible from Earth. Their enormous size often results in a lower surface temperature, which can diminish their apparent brightness despite their vast radii. This misconception can lead to confusion about the relationship between a star's size and its visibility. A further point of confusion revolves around the evolutionary stage of supergiants. Some assume that all supergiants are nearing the end of their life cycle or about to explode as supernovae. In truth, supergiants exist at various points in their evolutionary journey. UY Scuti, for example, is still in a relatively stable phase of its life, although it is destined for a dramatic future as it exhausts its nuclear fuel. Understanding these misconceptions illuminates the complexities inherent in studying such colossal celestial objects. Recognizing the nuances of supergiant stars helps us appreciate their true nature and the fascinating processes that govern their existence. As we delve deeper into the life cycle of massive stars, it becomes essential to clarify where UY Scuti fits within this cosmic narrative. The life cycle of a massive star like UY Scuti unfolds on a scale both grand and dramatic, marked by stages that span millions of years and culminate in spectacular finales. Unlike smaller stars, which gently fade into white dwarfs, massive stars burn brightly and briefly. Their lives characterized by rapid evolution, driven by intense nuclear fusion in their cores. Initially, these giants originate from colossal molecular clouds, vast regions of cold gas and dust, where gravity gradually coalesces matter into dense cores. As these cores gather mass, they ignite nuclear fusion, giving birth to a new star. For stars destined to become giants like UY Scuti, this birth process is swift and tumultuous, often shrouded in swirling nebulae that can be observed as stellar nurseries. Once formed, the star enters its main sequence phase, where it fuses hydrogen into helium in its core. For massive stars, this phase is relatively short-lived, lasting only a few million years, yet incredibly luminous. As hydrogen becomes depleted, the star's core contracts under gravity, igniting fusion in surrounding shells and causing the star's outer layers to expand dramatically. This is the stage where UY Scuti emerges, swelling into a red supergiant, a phase that marks its enormous size and luminosity. During this period, the star becomes unstable, shedding material through stellar winds and pulsations, enriching its surroundings with heavy elements, a process vital to cosmic chemical evolution. The final act of a massive star's life is marked by cataclysmic events. Depending on its remaining mass after shedding outer layers, UY Scuti would ultimately undergo a supernova explosion, leaving behind a neutron star, or black hole. This explosive death disperses elements forged in the star's core into space, seeding future generations of stars and planets. Throughout this cycle, UY Scuti represents a luminous, fleeting chapter, an evolved giant on the brink of its ultimate fate, embodying the dynamic and transformative nature of massive stellar evolution. This understanding of a star's life emphasizes the importance of initial conditions, like molecular cloud composition, which set the stage for such extraordinary stellar journeys. Now, the question arises, how do massive stars like UY Scuti form from their cosmic nurseries? Massive stars such as UY Scuti originate within the dense, cold regions of molecular clouds, vast interstellar nurseries composed primarily of hydrogen molecules, along with helium and trace elements. The process begins when localized regions within these clouds experience gravitational instabilities, often triggered by external influences like nearby supernova explosions or galactic shocks. As gravity gathers material, it causes the dense core to contract and heat up, initiating a runaway process that accelerates as more mass accumulates. This collapse eventually forms a protostar, a luminous object shrouded in a cocoon of gas and dust. During this early phase, the protostar's core temperature rises dramatically, reaching millions of degrees Kelvin. The surrounding dust and gas continue to accrete onto the core, increasing its mass and density. When the core temperature surpasses roughly 10 million Kelvin, hydrogen nuclei begin to fuse through nuclear processes, marking the star's transition onto the main sequence. For stars as massive as UY Scuti, this phase is characterized by rapid evolution compared to smaller stars due to their higher mass and luminosity. As the star stabilizes on the main sequence, hydrogen fusion becomes the dominant energy source. In such giants, the core temperature escalates further, enabling more complex fusion pathways. The dominant process is the CNO cycle, carbon-nitrogen-oxygen cycle, which is highly temperature-sensitive and efficient in converting hydrogen into helium in massive stars. This cycle proceeds rapidly, producing enormous amounts of energy that counteract gravitational collapse and sustain the star's enormous size. As UY Scuti exhausts its core hydrogen, the internal structure shifts and fusion processes become more complex. Helium nuclei fuse through different pathways depending on the core temperature and pressure, leading to the fusion of heavier elements such as carbon, oxygen, and eventually elements beyond. These stages involve a series of advanced fusion reactions that occur in shells surrounding the core, gradually building up heavier elements and prompting the star to expand further into its supergiant phase. Understanding these processes reveals how the star's internal chemistry evolves through its life, setting the stage for the dramatic transformations characteristic of its later stages. During its main sequence phase, UY Scuti primarily relies on the fusion of hydrogen into helium within its core, a process that sustains its immense luminosity and stability. This fusion occurs through the proton-proton chain reaction, which is most efficient in stars of moderate mass. However, given UY Scuti's extraordinary size and mass, the star's core conditions are extreme, leading to a more complex fusion environment. As the core heats up due to gravitational contraction, the CNO, carbon-nitrogen-oxygen, cycle becomes the dominant fusion mechanism. This cycle operates at higher temperatures and accelerates hydrogen burning, contributing significantly to the star's energy output. As UY Scuti exhausts its hydrogen fuel in the core, the fusion processes shift, marking the transition into later evolutionary stages. The core begins to contract under gravity, causing temperatures to soar and enabling the fusion of heavier elements, primarily helium. Helium fusion ignites through the triple alpha process, where 3 helium nuclei combine to form carbon, releasing substantial energy that temporarily halts the core's collapse. This phase is crucial in setting the stage for the star's expansion into a supergiant. In the star's outer layers, the increased energy production from helium fusion causes the outer envelope to expand dramatically, transforming UY Scuti into a luminous red supergiant. During this phase, fusion may proceed in shells around the core, with successive layers fusing heavier and heavier elements as the star evolves. This layered structure of shell fusion leads to complex pulsations and mass loss phenomena characteristic of supergiants. The intricate balance between these fusion processes and the star's enormous gravitational forces shapes its evolutionary path. The shift from hydrogen to helium and heavier element fusion signifies not only a change in internal energy production, but also a pivotal step toward eventual core collapse and supernova explosion. Understanding these processes provides insight into how UY Scuti's internal fusion activity drives its expansion into one of the universe's most majestic stellar giants. Next, exploring how the star's initial mass influences its lifespan and eventual transformation into a supergiant reveals the profound impact of these internal fusion mechanisms on its cosmic journey. The mass of UY Scuti plays a pivotal role in shaping both its lifespan and its evolutionary path. As a star of extraordinary size and mass, estimated to be around 10 to 20 times that of our Sun, its gravitational pull is immense, fueling rapid nuclear fusion processes in its core. This high mass accelerates the star's consumption of its nuclear fuel, resulting in a comparatively shorter lifespan for such a colossal object. While our Sun will remain stable for several billion years, a supergiant like UY Scuti burns through its fuel in a fraction of that time, often on the order of a few million years. This rapid consumption is a direct consequence of the star's immense core temperature and pressure, which intensify fusion reactions. Furthermore, the star's mass influences its evolutionary trajectory. Massive stars like UY Scuti experience more vigorous fusion rates, which cause them to expand dramatically as they exhaust their hydrogen core. As hydrogen fusion diminishes, the core contracts under gravity, heating up further and igniting new fusion shells around it. This process leads to the star swelling into a supergiant, with its outer layers stretching hundreds of times farther than its original size. The high mass also facilitates more advanced fusion stages, producing heavier elements such as carbon, oxygen, and eventually elements beyond iron in the later stages of evolution. The star's large mass not only determines the duration of its main sequence stage, but also influences the star's internal structure and the complexity of its layered composition. The balance between gravitational forces and radiation pressure shifts throughout its life, driving pulsations and instability that eventually contribute to its dramatic end. As UY Scuti approaches the final phases of its life cycle, its mass continues to dictate the nature of its death, potentially culminating in a spectacular supernova or even collapsing into a black hole. The profound impact of mass on UY Scuti's lifespan and evolution underscores the intricate relationship between a star's initial characteristics and its ultimate destiny. Understanding these connections provides crucial insights into how such titanic stars live, transform, and ultimately meet their fate. As UY Scuti matures, its internal architecture undergoes profound transformation, driven by ongoing nuclear processes and evolving equilibrium states. In its early stages, the star's core is primarily composed of hydrogen, fusing into helium through nuclear fusion, a process that generates the energy-balancing gravitational collapse. Over time, as the hydrogen supply diminishes, the core contracts under gravity, increasing in temperature and pressure. This contraction ignites shell burning around the core, where hydrogen fuses in a shell, causing the outer layers to expand dramatically and the star to swell into its enormous size. As UY Scuti ages, its internal structure becomes increasingly stratified. The core, now depleted of hydrogen, begins to fuse helium into heavier elements like carbon and oxygen. This shift alters the core's composition and density, leading to a core that is denser and hotter than earlier stages. Simultaneously, the outer envelope expands further, cooling as it extends outward, which causes the star's surface temperature to drop and its characteristic red hue to intensify. The outer layers become loosely bound and highly convective, facilitating the mixing of elements from the interior to the surface. This convective activity results in observable phenomena such as large-scale star spots and irregular brightness variations. Throughout these evolutionary phases, the star's internal pressure and gravity are in a delicate balance. As heavier elements accumulate in the core, the energy production rate and the star's radius fluctuate, resulting in periods of relative stability interspersed with more rapid changes. The star's composition becomes increasingly complex, with the outer layers enriched by elements dredged up from the interior during convective episodes. These compositional shifts have profound effects on the star's spectral characteristics, luminosity, and size. Understanding these structural and compositional transformations illuminates how a star like UY Scuti transitions from a massive main sequence star to an extraordinary red supergiant. This progression is not only a testament to stellar evolution but also to the intricate interplay of nuclear fusion, gravity, and convection that defines its life cycle. Yet, the precise moment when UY Scuti officially becomes a red supergiant remains a subject of scientific curiosity, prompting questions about the exact triggers of this dramatic transformation. UY Scuti's transformation into a red supergiant is a pivotal phase in its stellar evolution, driven by complex internal processes that unfold over millions of years. As the star exhausts the hydrogen fuel in its core through nuclear fusion, the delicate balance maintained by radiation pressure and gravity begins to shift. When hydrogen fusion diminishes, the core contracts under gravity's relentless pull, heating up significantly in the process. This core contraction causes the surrounding layers to expand outward, cooling as they do so, and the star's surface temperature drops. The star thus transitions from a relatively stable state into the massive luminous red supergiant that we observe. This expansion is not an abrupt event, but a gradual process triggered by core fusion dynamics and changes in the star's internal structure. As hydrogen fuel becomes scarce in the core, fusion shifts to the surrounding shells, generating increased energy that causes the outer layers to swell outward. The core's contraction continues until it reaches a temperature sufficient to ignite helium fusion, marking a new phase in the star's life cycle. During this transition, the star's outer envelope becomes vastly extended, its brightness peaks, and its surface cools to characteristic red hues. These changes are compounded by the star's enormous size and intricate internal reactions, which are influenced by its initial mass, composition, and rotation. The initiation of the red supergiant phase is thus a consequence of the core's evolving fusion processes and the star's response to the changing internal energy balance. It is a delicate interplay of nuclear physics and stellar dynamics, where the gradual depletion of hydrogen acts as the catalyst for the star's dramatic outward expansion. As UY Scuti approaches this stage, it exemplifies the grand evolutionary transformation that marks the end of its main sequence life and the beginning of its red supergiant phase, setting the stage for its eventual destiny as a supernova remnant or neutron star. Understanding these internal mechanisms offers vital clues about the star's future trajectory, which astronomers continue to refine through observations and modeling. Predicting the future evolution of a star as colossal and complex as UY Scuti requires a nuanced understanding of stellar physics, combined with sophisticated modeling techniques. Astronomers rely heavily on stellar evolution models, computational simulations that incorporate the star's current characteristics, such as mass, luminosity, surface temperature, and composition. These models are continually refined through observational data, including spectral analysis and measurements of brightness variations, which help constrain the star's current state and evolutionary stage. A critical component in these predictions involves understanding how UY Scuti's internal processes will change over time. As a red supergiant, UY Scuti is in a relatively advanced phase of its life cycle, with core fusion of heavier elements occurring in layers beneath its extensive outer envelope. The models project that, as nuclear fusion continues, the star will gradually exhaust its hydrogen fuel in the core, leading to core contraction and outer envelope expansion. This process results in increased luminosity and further expansion, pushing the star toward the upper limits of its stability. However, these models are not static. They incorporate factors such as mass loss through stellar winds, which dramatically influence the star's future. UY Scuti's immense size and luminosity drive powerful outflows of material from its outer layers. By estimating the rate of this mass loss, gleaned from spectroscopic signatures of stellar winds, astronomers can predict how quickly the star is shedding its outer envelope. This mass loss affects the star's evolution by reducing its total mass, altering the balance of internal pressures, and influencing the timeline and nature of its eventual demise. As UY Scuti approaches the end of its life, the interplay between core processes and outer mass loss becomes increasingly critical. The star's fate, whether it will culminate in a supernova explosion, collapse into a neutron star, or form a black hole, depends heavily on how much mass it retains at the point of core collapse. These predictions are inherently probabilistic, shaped by uncertainties in mass loss rates, internal mixing, and the physics of late-stage nuclear burning. Yet, through continual observations and refined models, astronomers edge closer to unveiling the ultimate destiny of this titanic star. Stellar winds and mass loss are fundamental processes that shape the evolution and ultimate fate of massive stars like UY Scuti. As UY Scuti ages, its outer layers become increasingly unstable, driven by intense radiation pressure and convective activity. These conditions generate powerful stellar winds, streams of charged particles expelled at tremendous velocities that carry away significant amounts of mass over time. This continuous shedding of material acts as a natural regulator, influencing the star's internal structure and its progression through later evolutionary stages. The rate of mass loss in stars like UY Scuti is far greater than in smaller stars, such as our Sun. In its luminous giant phase, the star can lose up to 1/1,000,000th of its solar mass each year, a seemingly small figure but substantial when accumulated over thousands of years. These winds are not uniform. They can be episodic, with periods of intensified outflow triggered by pulsations or thermal pulses within the star's interior. Such episodes can strip away vast portions of the star's outer envelope, exposing deeper layers and altering the star's surface composition. This process influences the star's brightness, temperature, and spectral characteristics, gradually transforming its appearance and spectral type. Mass loss also has profound implications for the star's future. As UY Scuti continues to shed its outer layers, it approaches the end of its life cycle, ultimately leading to the formation of a dense core, likely a neutron star or black hole, while the expelled material enriches the surrounding interstellar medium. The expelled matter, enriched with heavier elements forged in the star's core, contributes to the cosmic cycle of matter, providing material for new stars and planetary systems. Understanding stellar winds and mass loss in UY Scuti offers crucial insights into the complex processes governing the life cycle of the universe's most massive stars. These mechanisms do not merely mark the star's decline, they actively sculpt its destiny, influencing the environment around it and continuing the cycle of cosmic evolution. As we explore the star's grandeur, it's natural to wonder, what is the estimated radius of UY Scuti, and how does it compare to the size of our solar system? The sheer scale of UY Scuti is a testament to the astonishing diversity of stellar sizes within our, with a radius that spans approximately 1/700 times that of the Sun. This red hypergiant dwarfs most stars catalogued by astronomers. To put this into, if UY Scuti were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, encasing the entire inner planetary system and reaching well into the asteroid belt. Such a radius is not just a numerical curiosity. It is a physical marvel that defies everyday intuition about star sizes. When comparing UY Scuti to the solar system, the contrast is staggering. Our Sun, a relatively modest star by cosmic standards, has a radius of about 700 kilometers. UY Scuti's radius, on the other hand, exceeds 2.4 billion kilometers, enough to encompass the orbits of Mercury, Venus, Earth, Mars, and Jupiter combined. This means that if you could stand on the surface of UY Scuti, you'd be immersed in a landscape so vast that it would take years to traverse its expanse on foot. The star's enormous size also poses intriguing questions about its internal structure and stability, as such a vast volume must be balanced by complex processes of pressure and temperature. This colossal radius is intimately linked to the star's stage of evolution. UY Scuti is in a late phase of its life cycle, having expanded enormously as it exhausts its nuclear fuel. Its size is a transient feature, reflecting a delicate balance between gravitational forces pulling inward and radiation pressure pushing outward. Understanding the scale of UY Scuti provides a foundation for exploring its luminosity, energy output, and the physical processes that sustain such an extraordinary celestial body. As we delve into its brightness and energy emission, the star's remarkable dimensions will serve as a crucial backdrop for comprehending its place among the universe's most luminous giants. UY Scuti's extraordinary luminosity is a direct reflection of its colossal energy output, dwarfing most stars in the galaxy. Its brightness, measured at thousands of times that of our Sun, results from a combination of its immense size and the intense energy generated within its core. Unlike smaller stars, where energy escapes relatively easily, the vast surface area of UY Scuti means that even a modest temperature can produce an overwhelming amount of light. Its luminosity is so immense that if it were placed at the center of our solar system, it would illuminate the space out to the orbit of Jupiter or beyond, casting dramatic shadows and bathing neighboring planets in its radiance. This staggering brightness reveals much about the star's internal processes. UY Scuti is in a late stage of stellar evolution, fusing heavier elements in its core as it exhausts its hydrogen supply. The core's intense pressure and temperature facilitate nuclear reactions that release prodigious amounts of energy, which then radiates outward. The star's outer layers are expanded and tenuous, allowing this energy to escape over a vast surface area, amplifying its apparent brightness. Its luminosity also indicates a high mass, which correlates with rapid and powerful nuclear, sustaining such an enormous energy output over significant timescales. The star's glow is not uniform. It is influenced heavily by its surface temperature. This temperature, determining the star's color, is a key factor in the star's visible appearance. The combination of its size and energy release manifests as a luminous beacon that can be observed across great distances. The interplay between its energy production and surface conditions shapes UY Scuti's visual impression, making it not just a beacon of light, but a fascinating window into the complex processes that govern the life cycles of the universe's most massive stars. Understanding the star's brightness and energy output offers a glimpse into the powerful nuclear furnace at its core, setting the stage for deeper exploration of its surface characteristics and temperature. The surface temperature of UY Scuti plays a crucial role in shaping its visual characteristics and spectral appearance. Estimated to be around 3,500 to 4,0 Kelvin, this temperature places UY Scuti in the category of cool red supergiants. Such a relatively low surface temperature compared to smaller, hotter stars results in a distinctly reddish hue that dominates its vast expanse. This coloration is a direct consequence of blackbody radiation. Cooler objects emit light at longer wavelengths, predominantly in the red and infrared parts of the spectrum. As a result, UY Scuti radiates a soft, diffuse glow that can be observed with telescopes equipped with infrared sensors, revealing the star's warm outer layers. This cool temperature also influences the star's atmospheric composition and appearance. The lower thermal energy allows molecules like titanium oxide and vanadium oxide to form in the star's outer atmosphere, creating complex absorption features that further deepen its reddish coloration. These molecules contribute to the star's distinctive spectral signatures, which astronomers analyze to infer its temperature and chemical makeup. Consequently, UY Scuti appears as a luminous, ruby-red sphere, its surface shimmering with convective granules and turbulent flows driven by the intense radiation and massive size. Despite its immense luminosity, the star's relatively cool temperature means it radiates less energy per unit surface area than hotter stars like our Sun. Yet, due to its enormous surface area, spanning hundreds of times that of the Sun, its total brightness remains staggering. The interplay between its temperature and size creates a striking visual contrast, a star that is both luminous and surprisingly cool, giving it an otherworldly, tranquil glow. This temperature not only defines its color, but also influences the dynamics of its extended atmosphere, fostering the formation of vast convection cells and turbulent winds that shape its appearance and evolution over time. Understanding UY Scuti's surface temperature allows astronomers to grasp how such a colossal star can maintain stability and how its temperature-driven characteristics impact its spectral and visual identity. Moving from thermal properties, the next natural question involves how dense this behemoth is compared to smaller stars and what that means for its internal structure. While UY Scuti's immense size captures much of our imagination, its density reveals an equally fascinating aspect of its nature. Despite its enormous volume, so vast that it could comfortably contain hundreds of billions of times the volume of our Sun, its mass is surprisingly modest relative to its size. In fact, UY Scuti's average density is remarkably low, roughly a few hundred times less dense than water. To put this into perspective, the Sun's density is about 1.4 grams per cubic centimeter, while UY Scuti's density hovers around a fraction of a gram per cubic centimeter. This stark contrast underscores a fundamental principle of stellar physics. As stars grow in size, especially into supergiant proportions, their outer layers expand dramatically, causing their overall density to plummet. This low density has profound implications for the star's internal structure and evolutionary trajectory. Unlike compact stars such as white dwarfs or neutron stars, UY Scuti's material is dispersed over an enormous volume, with its core still undergoing nuclear fusion processes that counteract gravitational collapse. The tenuous outer atmosphere is so diffuse that it extends far beyond the core, creating a vast, tenuous envelope that is vulnerable to stellar winds. These winds carry away mass over time, gradually shrinking the star's outer layers and influencing its lifespan and future evolution. The star's density also impacts its stability and energy output. The thin, expansive envelope facilitates the pulsations observed in many red supergiants, leading to variability in brightness. These pulsations are driven by complex interactions between the star's expansive outer layers and its core's nuclear activity. As UY Scuti continues to evolve, its low density will play a crucial role in determining how rapidly it sheds mass, how it transitions through different evolutionary stages, and ultimately, how it nears the end of its life cycle. Understanding the density of such a colossal star invites deeper questions about its fundamental properties, particularly how its mass compares to our Sun and how that mass influences its ongoing evolution. This naturally leads us to examine the star's mass relative to our familiar solar benchmark. UY Scuti's staggering mass, estimated to be around 7 to 10 times that of our Sun, plays a pivotal role in shaping its extraordinary characteristics and ultimate destiny. While this might seem modest compared to its immense size, the star's mass influences the internal pressures and temperatures that drive its fusion processes. In giants like UY Scuti, the greater mass results in more vigorous fusion reactions in their cores, which in turn produce the enormous luminosity and size observed. This mass also influences the star's lifespan. Despite its size, UY Scuti's relatively modest mass compared to more massive supergiants means it will spend a few million years in its current luminous phase before exhausting its nuclear fuel. The relationship between mass and stellar evolution is intricate. A star's mass determines how quickly it consumes its hydrogen core fuel, which impacts its transition into later stages of evolution, such as expanding into a red supergiant and eventually shedding its outer layers. For UY Scuti, its mass signifies that it is well into its advanced evolutionary phase, characterized by a bloated outer envelope and a cool surface temperature. Its substantial size results from the balance of gravity and radiation pressure in its outer layers, a dynamic directly linked to its mass. Over time, as UY Scuti exhausts its nuclear fuel, it will likely undergo dramatic changes, possibly ending as a supernova or collapsing into a neutron star or black hole, depending on the remaining mass after its outer layers are expelled. Understanding how mass influences a star's evolution offers crucial insights into its past and future. It provides context for the star's current state, revealing the processes that sustain its luminosity and size. Equally important is recognizing that mass is not the sole factor. Internal composition and external influences also shape a star's life cycle. With this foundation, astronomers turn their attention to deciphering the star's chemical makeup, unlocking further secrets of UY Scuti's nature and the complex processes that govern its existence. Determining the composition of a distant star like UY Scuti involves sophisticated techniques rooted in spectroscopy, which allows astronomers to analyze the star's light and infer its chemical makeup. When UY Scuti's light reaches Earth, it carries a wealth of information encoded in its spectrum, a detailed fingerprint of the elements present in the star's atmosphere. By dispersing this light through spectrographs, scientists obtain spectra that display absorption lines, dark bands corresponding to specific wavelengths where atoms and molecules absorb light. Each element has a unique set of spectral lines, serving as a signature that can be identified with high precision. In the case of UY Scuti, astronomers focus on the prominent absorption features caused by elements such as hydrogen, helium, carbon, nitrogen, oxygen, and trace metals. The relative strength and shape of these lines provide clues not only about which elements are present, but also about their abundance within the star's outer layers. For instance, the Balmer series of hydrogen lines reveals the presence and temperature of the star's atmosphere, while lines of heavier elements inform about nucleosynthesis processes and chemical enrichment. High-resolution spectroscopy is essential for disentangling overlapping lines and accounting for broadening effects caused by stellar winds and turbulence. Since UY Scuti is a luminous red supergiant with extensive mass loss, the spectral lines are often broadened or shifted, complicating the analysis. To address this, astronomers compare observed spectra with synthetic models generated through stellar atmosphere simulations, which incorporate various parameters to match the data accurately. Additionally, advances in infrared spectroscopy expand the capacity to probe cooler and dust-enshrouded regions of UY Scuti, revealing elements that may be obscured at visible wavelengths. Combining data across different spectral ranges enables a comprehensive understanding of the star's chemical composition, shedding light on its evolutionary history and the processes occurring in its vast outer layers. These techniques collectively paint a detailed picture of what elements comprise UY Scuti and how they influence its current state. The atmosphere of UY Scuti is a vast, dynamic environment characterized by complex layers of gas and dust that extend far beyond the star's core. As a red hypergiant, its outer envelope is composed primarily of hydrogen and helium, with traces of heavier elements that contribute to its distinctive spectral signature. These layers are not static. They are subject to continuous turbulence driven by convection currents and pulsations within the star. Such activity results in a highly uneven and mottled appearance when observed in detail, with regions of varying temperature and density. These fluctuations influence the star's luminous output, causing subtle shifts in brightness that reflect ongoing internal processes. Stellar winds emanating from UY Scuti are among the most prodigious known in the universe. These powerful outflows are driven by the star's intense radiation pressure and the energy from convective motions within its outer layers. The winds carry away mass at an astonishing rate, creating a circumstellar environment rich in gas and dust particles that gradually disperse into space. This mass loss is not uniform. It features clumps and episodic enhancements, likely caused by pulsational instabilities and magnetic activity. As these winds interact with the surrounding interstellar medium, they form complex nebulae that can stretch across vast regions, contributing to the enrichment of the galaxy with heavy elements. The combination of turbulent atmospheres and vigorous stellar winds makes UY Scuti a prime example of a star in a highly active phase of its evolution. The processes shaping its atmosphere and winds are essential to understanding the life cycle of massive stars. They also influence the star's observable characteristics, including variability in brightness and spectral features. Recognizing these features provides a glimpse into the fundamental mechanisms at play in hypergiants like UY Scuti. As we look deeper, questions naturally arise about how these properties change over time, especially given the star's enormous size and energetic processes. This leads us to consider: how does the size and brightness of UY Scuti fluctuate over time, if at all? UY Scuti's immense size and luminosity are not static attributes. Rather, they exhibit subtle fluctuations over time, characteristic of many red supergiant stars. These variations are primarily driven by complex internal processes, including pulsations within the star's outer layers. As the star's core fuses elements and generates energy, the resulting pressure causes the outer layers to expand and contract rhythmically. During expansion phases, UY Scuti's radius increases slightly, making the star appear larger and more luminous. Conversely, during contraction, its apparent size and brightness diminish marginally. These pulsations are irregular in both amplitude and period, often occurring over spans of hundreds of days to several years. Astronomers have observed that the star's brightness can fluctuate by a few tenths of a magnitude, enough to be detected with precise photometric measurements. These brightness variations are not merely cosmetic. They reflect the dynamic and turbulent processes occurring within the star's interior. The star's outer envelope is semi-unstable, with convection cells and shock waves propagating through its vast layers, contributing to these irregular pulsations. While the overall luminosity of UY Scuti remains extraordinarily high, outshining many stars in our galaxy, the subtle shifts over time are a testament to its volatile nature. Monitoring these fluctuations provides valuable insights into the life cycles of red supergiants and their eventual fate as supernovae. The star's pulsations are also linked to mass loss episodes, where giant stellar winds carry away material into space, gradually shaping UY Scuti's future evolution. These ongoing variations underscore the complexity of such colossal stars, illustrating that even the most seemingly stable giants are, in fact, dynamic and ever-changing. As we move from understanding its internal behavior, a natural next step is to consider where UY Scuti resides within the vast expanse of our galaxy and how its position relates to our vantage point on Earth. Nestled within the sprawling arms of our Milky Way galaxy, UY Scuti occupies a relatively distant yet intriguing position. To appreciate its location, it's essential to understand the structure of our galaxy. The Milky Way is a barred spiral galaxy with a dense central core surrounded by several spiral arms extending outward. UY Scuti resides somewhere along the Scutum Centaurus arm, one of the galaxy's prominent spiral arms, approximately 9,500 light-years away from Earth. This considerable distance places it far beyond our solar neighborhood, emphasizing the vast scale of our cosmic environment. Positioned in the constellation Scutum, UY Scuti is part of a dense stellar region rich with other luminous giants and variable stars. Its placement within this arm means that, although it appears as a bright point of light in our sky, it is actually located in a far-flung, relatively obscure part of the galaxy. Its position relative to Earth is not just a matter of distance, but also of orientation. From our vantage point, UY Scuti's light takes thousands of years to reach us, traveling across interstellar dust and gas that partially obscure and influence the observed brightness. The star's location is mapped through a combination of astronomical surveys and detailed star charts, which include information gleaned from both optical and infrared observations. These data help astronomers pinpoint its position within the galactic plane and its relative distance from the Sun. While the precise coordinates are constantly refined, the key takeaway is that UY Scuti resides in a relatively remote part of the galaxy, making it a fascinating target for understanding stellar evolution in the outer stellar neighborhoods of the Milky Way. Understanding its position also sets the stage for the next challenge. How do scientists determine the exact distance to such a distant, luminous object with remarkable accuracy? This question leads us into sophisticated measurement techniques that have revolutionized our ability to chart the cosmos with unprecedented precision. Measuring the distance to UY Scuti with remarkable precision involves a combination of advanced observational techniques and meticulous data analysis. Since UY Scuti resides many thousands of light-years away, direct measurement methods are not feasible. Instead, astronomers rely on indirect methods that leverage the star's intrinsic properties and its apparent behavior from Earth. One primary approach is the use of parallax measurements, which involve observing the star's apparent shift in position against background stars as Earth orbits the Sun. For nearby stars, this method provides highly accurate distances. However, UY Scuti's vast distance renders its parallax angle exceedingly small, so minute that even the most precise ground-based telescopes struggle to detect it reliably. To overcome this, astronomers utilize space-based observatories like the Gaia satellite, which are equipped with cutting-edge instrumentation capable of measuring tiny stellar positional shifts with micro-arcsecond precision. Gaia's data has been instrumental in refining the distance estimates for many distant stars, including UY Scuti, by analyzing its parallax over several years. Beyond parallax, astronomers often employ spectroscopic techniques to determine the star's luminosity class and temperature. By analyzing the star's spectrum, they can estimate its intrinsic brightness. Comparing this with the star's observed brightness from Earth, corrected for interstellar extinction, allows for the calculation of its distance through the inverse square law of light. This approach depends heavily on accurate models of stellar atmospheres and assumes the star's properties align with those predicted by stellar evolution theories. Another complementary method involves studying variable stars within the same region or using known standard candles, such as Cepheid variables, if present. These stars have well-established relationships between their pulsation periods and luminosities, providing an independent measure of distance. Combining these methods, parallax, spectroscopy, and standard candles, enables astronomers to cross-verify and refine the distance estimates for UY Scuti, pushing the boundaries of observational precision despite the star's remoteness. Determining the precise distance to stars like UY Scuti presents a host of intricate challenges that continue to test astronomers' ingenuity. As one of the most luminous and expansive red supergiants known, UY Scuti resides thousands of light-years away, making direct measurement approaches difficult. Traditional methods, such as parallax measurements, rely on observing the apparent shift of a star against background objects as Earth orbits the Sun. For relatively nearby stars, this technique yields accurate results. But at the vast distances involved with UY Scuti, the parallax angle becomes minuscule, often too small to measure reliably with existing instruments. Advancements in technology, such as space-based observatories like Gaia, have pushed the boundaries of parallax measurement. Yet even these sophisticated systems encounter limitations when dealing with extremely distant, luminous giants. The star's immense size and brightness can introduce additional complexities. Its extensive atmosphere and variability can distort measurements, especially since the star's outer layers are dynamic, with pulsations and convective motions that influence its apparent position and brightness over time. Alternative methods, including spectroscopic parallax, involve analyzing the star's spectral characteristics to estimate its intrinsic luminosity and, consequently, its distance. However, this approach hinges on accurate models of stellar atmospheres and evolutionary stages, which can be uncertain for such massive and variable stars. Interstellar dust and gas further complicate matters by absorbing and scattering light, causing extinction that can lead to underestimating the star's true brightness and skewing distance calculations. All these factors create a web of uncertainties, making the task of pinpointing UY Scuti's exact location a persistent challenge. Each incremental refinement in measurement techniques, however, enhances our understanding and brings us closer to resolving the star's precise position in the cosmos. As we refine these measurements, a clearer picture emerges not only of UY Scuti itself, but also of the broader structure of our galaxy. Understanding the star's true distance offers vital clues to the spatial layout of the Milky Way, revealing insights into its size, shape, and the distribution of its most massive stellar inhabitants. UY Scuti's placement within the Milky Way provides valuable insights into the galaxy's complex architecture and the distribution of its most massive stars. Situated in the constellation Scutum, roughly 9,500 light-years from Earth, its location is not arbitrary, but rather part of a broader stellar tapestry that reveals the patterns of star formation and galactic structure. This positioning situates UY Scuti within one of the galaxy's spiral arms, a region rich in gas and dust that serve as nurseries for new stars. Its placement helps astronomers map the spiral arm's extent and density, shedding light on the processes that shape the Milky Way's morphology. The identification of UY Scuti in this specific region also aids in understanding the life cycle of massive stars within the galactic environment. By analyzing its position relative to other stellar populations and star-forming regions, researchers can infer the conditions that give rise to such colossal stars. These giants tend to cluster in areas of recent or ongoing star formation, suggesting that their emergence is closely linked to the availability of molecular clouds and the dynamics of spiral arm density waves. Furthermore, UY Scuti's location contributes to the calibration of distance measurement techniques such as parallax and spectroscopic parallax within our galaxy. Precise knowledge of its position allows astronomers to refine models of stellar luminosity and size, which are essential for understanding the broader galactic scale. Its placement also provides a reference point for mapping the three-dimensional structure of the Milky Way, aiding in the construction of more accurate models of its spiral arm configuration and overall mass distribution. In essence, UY Scuti's position acts as a vital puzzle piece in the grand design of our galaxy. Its strategic location helps astronomers decipher the intricate patterns of star formation, the distribution of stellar populations, and the structural contours of the Milky Way itself. This understanding is fundamental to grasping not only the galaxy's current state, but also the dynamic processes that continue to shape its evolution over cosmic timescales. UY Scuti's location within the galaxy offers a unique vantage point for understanding the broader processes that shape stellar and galactic. Situated in the constellation Scutum, this colossal star resides near the outer regions of the Milky Way, a position that provides insight into the distribution and life cycle of the most massive stars in our galaxy. Its placement contributes to our understanding of the galactic environment in which such giants form and evolve, shedding light on the conditions conducive to their development. As a red supergiant, UY Scuti exemplifies a late stage in stellar evolution, illustrating the fate awaiting massive stars after their main sequence phase. Its position allows astronomers to study the remnants of star formation regions and the influence of massive stars on their surroundings. The intense stellar winds and eventual supernova explosions from stars like UY Scuti play a crucial role in enriching the interstellar medium with heavy elements, which are fundamental for subsequent generations of star and planet formation. Observing its location helps map how these processes are distributed throughout the galaxy, revealing patterns of stellar birth and death cycles. Furthermore, UY Scuti's placement aids in refining models of galactic dynamics. Its motion relative to the galactic core and neighboring stars can illuminate the gravitational influences shaping the Milky Way's structure. This, in turn, enhances our understanding of how mass, dark matter, and stellar populations are distributed across the galaxy. The star's position also intersects with regions of active star formation, providing context for the environmental conditions that foster the emergence of such extraordinary giants. Studying UY Scuti within its galactic habitat underscores the interconnectedness of stellar evolution and galactic architecture. Its considerable size and advanced evolutionary stage serve as a reminder of the immense scale and complexity of cosmic processes operating over millions to billions of years. Understanding its location helps astronomers piece together the intricate puzzle of how massive stars influence and are influenced by the galaxy's ongoing evolution. This exploration naturally leads to an examination of the methods used to measure distances to stars like UY Scuti, highlighting the importance of precise techniques in unveiling the star's true nature and role within the galaxy. Measuring the immense distance to UY Scuti requires a nuanced application of several astronomical techniques, each with its own strengths and limitations. Parallax measurement. The most direct method for nearby stars involves observing the apparent shift of the star's position against distant background objects as Earth orbits the Sun. For stars thousands of light-years away like UY Scuti, this shift becomes vanishingly small, pushing the limits of current instrumentation. Missions such as Gaia have improved parallax accuracy, yet at such vast distances, the tiny angular displacements introduce significant uncertainties, making this method less reliable on its own. Complementing parallax are brightness-based methods, notably the period luminosity relationship used for variable stars. As a red supergiant, UY Scuti's luminosity varies over time. By analyzing its pulsation period, astronomers infer an intrinsic luminosity, which, when compared with observed brightness, yields an estimate of its distance. This approach hinges on the assumption that the star's pulsations are well understood and consistent, but uncertainties in the star's pulsation mode and potential deviations can affect accuracy. Another critical method involves spectroscopic parallax, where spectral features provide clues about the star's size and intrinsic brightness. Combining spectral analysis with models of stellar atmospheres allows for another distance estimate, though this method depends heavily on the precision of the models and the star's atmospheric properties. Cross-referencing these techniques often reveals discrepancies, underscoring the challenges inherent in studying such distant, luminous giants. The inherent uncertainties in each method mean astronomers must carefully synthesize multiple lines of evidence, often arriving at a consensus distance that balances the strengths and weaknesses of each technique. This intricate web of measurements highlights the importance of understanding the environment surrounding UY Scuti. As we refine our distance estimates, one factor remains persistent: the interstellar medium. Dust and gas lurking between us and the star complicate our observations, casting a veil that can distort brightness measurements and spectral data. Recognizing how these cosmic clouds influence our view is crucial for honing our understanding of UY Scuti's true nature and position in the universe. Interstellar dust and gas serve as both the universe's veils and its storytellers, intricately shaping our perception of celestial giants like UY Scuti. These cosmic materials, composed primarily of tiny particles of carbon, silicates, and other elements, are dispersed unevenly throughout the galaxy, often forming dense clouds that obscure the light from objects lying behind or within them. When astronomers attempt to observe UY Scuti, these dust clouds act as filters, scattering and absorbing a significant portion of the star's emitted light. This interference complicates efforts to measure the star's true brightness and distance with precision. The starlight that eventually reaches Earth-based telescopes has often traversed multiple layers of dust, which can distort the apparent luminosity and color. This phenomenon, known as interstellar extinction, makes UY Scuti appear dimmer and redder than it actually is, leading to uncertainties in its estimated size and position. Additionally, gas clouds in the star's vicinity or along our line of sight can introduce further distortion, sometimes mimicking the effects of distance or size variations that are not actually present. The challenge lies in disentangling the star's intrinsic light from the effects of this intervening medium. Spectroscopic observations help by analyzing how dust and gas modify the star's spectrum, revealing clues about the composition and density of the obscuring material. By understanding these effects, astronomers can apply corrections to their measurements, gradually refining the star's known parameters. Nevertheless, the patchy distribution of dust and gas in the galaxy continues to pose limitations, leaving some ambiguity around the precise nature and location of UY Scuti. As technology advances, astronomers are continuously seeking better ways to peer through these cosmic veils. The development of more sensitive instruments and innovative observation techniques promises to reduce the impact of interstellar obscuration, bringing us closer to uncovering the true details of UY Scuti's position and properties. This ongoing quest underscores the dynamic relationship between the universe's complexity and our ever-improving capacity to understand it. Advancements in telescope technology promise to significantly refine our understanding of UY Scuti's precise position within the cosmos. Current measurements rely heavily on parallax techniques, which, while effective for many stars, encounter challenges when applied to distant, expansive objects like supergiants. The primary obstacle lies in the star's immense size and the subtle shifts in position that are difficult to detect over vast distances. Future telescopes, equipped with enhanced angular resolution and sensitivity, are poised to overcome these limitations. Next-generation space-based observatories, such as the James Webb Space Telescope, JWST, and planned missions like the European Space Agency's Gaia successor, are expected to deliver unprecedented astrometric precision. Gaia, in its current form, has already revolutionized our stellar maps by measuring stellar positions with micro-arc-second accuracy. Future missions will build upon this foundation, employing advanced detectors and refined calibration techniques to track even minute positional changes in stars like UY Scuti. These improvements will allow astronomers to determine its distance with greater certainty, reducing uncertainties that currently stem from parallax measurement constraints. Complementary innovations in interferometry, combining signals from multiple telescopes across large distances, will enable astronomers to achieve ultra-high resolution imaging. This technique can resolve the star's disk with extraordinary detail, revealing subtle positional shifts over time. Such detailed observations will not only improve distance estimates, but also enhance our understanding of the star's atmospheric dynamics and surface features, which can influence positional measurements. Additionally, adaptive optics systems integrated into ground-based telescopes will mitigate atmospheric distortions, allowing for sharper images and more reliable astrometric data. As these technologies evolve, they will facilitate continuous, high-precision monitoring of UY Scuti's position, contributing to a more accurate three-dimensional placement within our galaxy. Together, these technological advancements will deepen our grasp of UY Scuti's cosmic coordinates, laying a more solid foundation for subsequent studies. This progress in pinpointing its location underscores the importance of continual innovation in observational astronomy, each step bringing us closer to unraveling the complexities of the universe. UY Scuti's prominence as a benchmark in the study of supergiant stars stems from its extraordinary size and luminosity, which push the boundaries of our understanding of stellar physics. As one of the largest known stars, its sheer scale provides a unique laboratory for testing models of stellar structure and behavior at the extreme end of the stellar mass spectrum. Its immense radius, estimated to be over 1/700 times that of the Sun, challenges existing theories about how stars can sustain themselves without collapsing under their own gravity. The star's brightness, coupled with its size, also offers insights into the complex processes governing energy production and transport within such colossal objects. In addition, UY Scuti's variability and spectral characteristics serve as crucial data points. Its pulsations reveal how massive stars undergo internal oscillations, which influence their outer layers and contribute to mass loss, an essential factor in their evolution. By studying these pulsations, astronomers gain a better understanding of the dynamic processes occurring deep within supergiants, which are often difficult to observe directly. The star's spectral signatures, influenced by its extensive atmosphere and stellar winds, provide clues about the composition and physical conditions present in these distant giants. Furthermore, UY Scuti acts as a reference point for calibrating models of stellar evolution, especially for stars nearing the end of their life cycle. Its properties help refine predictions about how massive stars grow, lose mass, and eventually transition into supernovae or other compact remnants. Because of its well-documented characteristics, UY Scuti enables astronomers to compare observations with theoretical models, validating or challenging our current understanding of stellar life cycles. Studying such an extraordinary star not only enhances our grasp of individual stellar phenomena, but also informs broader astrophysical contexts. It aids in understanding the life cycle of the most massive stars, the mechanisms behind their dramatic endings, and their influence on galaxy evolution. As we delve into how UY Scuti's properties reveal the processes governing stellar death, its role as a cosmic benchmark becomes even more profound. Studying UY Scuti offers critical insights into the complex processes governing stellar evolution, particularly for the most massive stars. As a red supergiant nearing the final stages of its life cycle, UY Scuti exemplifies a phase where stars have exhausted the fuel in their cores, leading to dramatic structural changes. Observations of such stars allow astronomers to refine models of how massive stars evolve over millions of years, transitioning from stable hydrogen fusion to unstable, pulsating states that precede core collapse. The star's extended atmosphere and massive size serve as a natural laboratory for understanding mass loss mechanisms, key factors influencing a star's ultimate fate. UY Scuti's intense stellar winds and episodic eruptions shed vast amounts of material into space, contributing to the enrichment of the interstellar medium and setting the stage for subsequent generations of stars and planets. Furthermore, the star's internal structure and pulsations provide clues about the late-stage nuclear processes occurring within. By analyzing its brightness variations and spectral properties, scientists gain a window into the complex fusion reactions and convection currents that drive a star toward its end. These insights are vital because they help predict how similar stars might behave as they approach supernova explosions or other death scenarios. UY Scuti's massive size and luminosity also influence the surrounding environment, affecting the dynamics of nearby interstellar matter and star formation regions. As a case study, UY Scuti emphasizes the importance of accurately modeling mass loss, energy transport, and core collapse in massive stars. Its properties challenge existing theories and push astronomers to develop more sophisticated simulations. By understanding the life cycle of such gigantic stars, scientists can better predict the types of supernovae they produce, the remnants they leave behind, neutron stars or black holes, and their role in shaping galactic evolution. Each observation of UY Scuti brings us closer to deciphering the complex tapestry of stellar death, revealing not just the final moments of individual stars, but also the broader cosmic processes at play. UY Scuti's extraordinary dimensions push the boundaries of what astronomers consider possible for stellar giants, offering critical insights into the upper limits of star size and luminosity. Its immense radius, estimated to be over 1/700 times that of our Sun, raises fundamental questions about the physical processes that sustain such colossal structures. In particular, UY Scuti exemplifies the delicate balance between gravitational forces pulling inward and the outward pressure exerted by nuclear fusion and radiation. This equilibrium, known as hydrostatic stability, becomes increasingly tenuous at these scales, prompting researchers to examine whether there is a natural cap to how large a star can grow before it becomes unstable or disperses. Luminosity, closely tied to a star's size, also reaches extraordinary levels in UY Scuti's case. Despite its vast size, its brightness is relatively moderate compared to some other luminous red variables, hinting at complex internal processes that regulate energy output. This relationship suggests that beyond a certain point, increasing a star's size does not necessarily equate to proportional increases in brightness, challenging earlier assumptions that larger stars are always more luminous. Instead, UY Scuti demonstrates that factors such as surface temperature, stellar composition, and mass loss through stellar winds profoundly influence the star's luminosity, shaping a nuanced picture of stellar extremes. Furthermore, UY Scuti's characteristics serve as a natural laboratory for testing theoretical models of stellar evolution at the upper limits. Its existence prompts re-evaluation of the mass thresholds where stars transition from stable giants to supergiants, or even supermassive stars potentially destined to become black holes. The star's measurable properties help refine models regarding how massive stars shed material over their lifetimes, preventing unbounded growth and influencing their ultimate fate. As a luminous red supergiant, UY Scuti exemplifies the complex interplay of forces that define the upper thresholds of stellar size and brightness. Its study illuminates the physical constraints that govern the life cycles of the universe's most massive stars, providing essential clues about the nature of stellar limits and the processes that shape their evolution. UY Scuti's extraordinary size and luminosity serve as a crucial test for the boundaries of current stellar physics, challenging and refining existing theories about the life cycles and internal processes of massive stars. Traditional models of stellar evolution predict that stars of such immense scale should encounter instabilities as they approach the supergiant phase. The sheer volume of UY Scuti's outer layers, combined with its intense radiative output, raises questions about the stability of these extended atmospheres and the physical mechanisms that sustain them. One key aspect that UY Scuti prompts scientists to reconsider is the nature of the star's internal convection and energy transport. Its vast size suggests an extensive convective zone, which must efficiently transfer energy from the core to the surface. Observations, however, reveal complex surface dynamics, including pulsations and irregular brightness variations, hinting at turbulent convection and possibly non-uniform mass loss. These phenomena challenge simplified models that assume steady, symmetric stellar winds, indicating that the internal workings of supergiants may be more chaotic than previously thought. Additionally, UY Scuti's existence influences theories regarding the upper mass limits of stars and their resultant end states. Its mass loss rate, driven by intense stellar winds, plays a decisive role in determining whether such a star will eventually explode as a supernova or collapse into a black hole. The star's extreme parameters suggest that mass loss mechanisms could be more variable and episodic, complicating predictions of supernova progenitors. This variability, observed through irregular brightness fluctuations and spectral signatures, encourages revisions to models of late-stage stellar evolution, especially concerning how massive stars shed their outer envelopes. Furthermore, UY Scuti challenges the understanding of the physical limits of stellar size and luminosity. While some theories posit an upper boundary defined by radiation pressure and gravitational stability, the star's existence hints at the possibility that these boundaries may be more flexible, possibly influenced by metallicity and other environmental factors. Its characteristics push astrophysicists to refine the equations governing stellar structure, ensuring they accommodate the extremes exemplified by UY Scuti. In effect, UY Scuti acts as both a benchmark and a catalyst for advancing stellar physics, prompting ongoing research into the complex, dynamic processes that define the lives of the universe's most colossal stars. Supergiant stars such as UY Scuti exert a profound influence on their surrounding interstellar environment, shaping the very fabric of the galaxy in which they reside. These stellar behemoths are characterized by intense radiation, powerful stellar winds, and episodic mass ejections, all of which contribute to a dynamic and often turbulent cosmic neighborhood. The immense luminosity of UY Scuti results in a high-energy radiation field that can ionize nearby gas clouds, creating expansive H2 regions. These ionized zones glow brightly and serve as beacons of star formation activity. The radiation pressure from such luminous giants can also exert a feedback effect, dispersing surrounding molecular clouds and halting further star formation in some regions. Conversely, the shock waves generated by the star's variable winds and eruptions can compress adjacent gas, triggering the collapse of dense regions and catalyzing new generations of stars. This duality, where the star both inhibits and promotes star formation, makes supergiants like UY Scuti central figures in the ongoing evolution of the interstellar medium. Stellar winds from UY Scuti are particularly influential, carving out cavities in the interstellar medium known as bubbles. These structures are filled with hot, diffuse gas, heated by shock interactions, observable in various wavelengths such as X-ray and radio emissions. Over time, the accumulation of ejected material enriches the surrounding medium with heavy elements synthesized within the star's core. When the star eventually reaches the end of its life cycle, the supernova explosion, if it occurs, would inject a vast amount of energy and newly formed elements into the interstellar environment, further shaping future star formation and galactic chemical evolution. Understanding how supergiants like UY Scuti interact with their surroundings offers crucial insights into the complex feedback mechanisms that govern galaxy dynamics. Their influence extends beyond immediate stellar neighborhoods, impacting the large-scale structure and composition of the galaxy itself. Such stars act as both creators and destroyers within the cosmic cycle, illustrating the intricate interplay between stellar evolution and the galactic ecosystem. This exploration naturally leads to a broader question. What role does UY Scuti play in understanding the life cycle of massive stars in the galaxy? UY Scuti serves as a vital reference point in unraveling the complex evolutionary pathways of massive stars within our galaxy. Its extraordinary size and luminosity provide astronomers with a rare opportunity to observe and analyze the late stages of stellar development in high-mass stars, which are otherwise difficult to study in detail due to their relative rarity and rapid evolution. By examining UY Scuti's spectral characteristics, scientists gain insight into the physical processes that dominate the supergiant phase. Its extended atmosphere and mass loss phenomena reveal how massive stars shed their outer layers, enriching the interstellar medium with heavy elements that are essential for subsequent generations of star formation. These mass loss episodes influence the star's ultimate fate, determining whether it will end as a neutron star or collapse into a black hole, often following a spectacular supernova explosion. Moreover, studying UY Scuti enhances our understanding of the transition phases that precede stellar death. Its position on the Hertzsprung-Russell diagram, along with its variability patterns, helps map the evolutionary trajectory of massive stars, providing clues about the timescales and physical conditions involved. Observations of its pulsations and surface phenomena contribute to refining models of stellar structure and energy transport in supergiants, which are pivotal for accurate simulations of stellar evolution. In addition, UY Scuti's properties serve as benchmarks for calibrating theoretical models of stellar life cycles. By comparing its observed characteristics with those predicted by models, researchers can identify discrepancies and improve the underlying physics, such as opacities, convection processes, and wind dynamics. These refinements have broader implications, influencing how astronomers interpret the life histories of similar stars in different environments across the galaxy. Ultimately, UY Scuti acts as both a luminous laboratory and a cosmic yardstick, illuminating the life stories of the galaxy's most massive stars. Its study continues to deepen our grasp of stellar evolution, helping to piece together the intricate tapestry of stellar and galactic development. UY Scuti's immense size and brightness serve as a vital benchmark in our quest to understand the vastness of the universe. As one of the largest known stars, accurately measuring its distance helps refine the cosmic distance scale, a crucial framework that enables astronomers to estimate how far objects are across the universe. Determining UY Scuti's distance involves sophisticated techniques such as parallax measurements, which observe the star's apparent position shifts relative to distant background objects as Earth orbits the Sun. Although parallax is challenging for such distant and luminous giants, advancements in instrumentation, including space-based telescopes like Gaia, have improved the precision of these measurements. By establishing a reliable distance to UY Scuti, scientists can calibrate luminosity benchmarks for other luminous stars, aiding in the construction of a more accurate distance ladder. This calibration process is fundamental because UY Scuti's brightness, combined with its known distance, allows researchers to determine its true luminosity and size with greater certainty. These parameters are essential for testing stellar evolution models, especially for the most massive and luminous stars. Understanding the limits of stellar size and brightness directly informs theories about how stars form, evolve, and ultimately end their lives. Moreover, UY Scuti's role as a luminous beacon helps astronomers gauge the scale of distant galaxies, as similar supergiant stars are often used as standard candles or reference points in extragalactic observations. In essence, UY Scuti acts as a cosmic ruler that helps bridge our local stellar measurements with the broader universe. Its study not only refines our grasp of individual stellar properties, but also enhances the accuracy of the cosmic distance scale. This, in turn, influences our understanding of the universe's expansion rate, the distribution of galaxies, and the fundamental parameters that shape cosmology. As we continue to refine our measurements of such colossal stars, we deepen our comprehension of the universe's structure and scale, paving the way for more profound cosmological insights. The investigation of UY Scuti extends far beyond understanding a single, extraordinary star. It offers profound insights into the fundamental processes shaping the universe. As one of the largest known stars, UY Scuti serves as a natural laboratory for exploring the upper limits of stellar evolution, mass loss, and the life cycle of massive stars. These processes are critical for comprehending how stars influence their surrounding environments, enrich the interstellar medium, and ultimately contribute to the formation of new celestial bodies. Studying such colossal stars pushes current theoretical models to their boundaries, revealing potential gaps in our understanding of stellar physics, especially regarding how stars can sustain such immense sizes without dispersing or collapsing prematurely. Furthermore, insights gleaned from UY Scuti inform broader cosmological questions. For example, understanding the end stages of massive stars like UY Scuti helps refine models of supernova explosions and the formation of black holes and neutron stars. These phenomena play pivotal roles in galaxy evolution by distributing heavy elements and shaping the interstellar landscape. In addition, the extreme conditions present in UY Scuti challenge existing theories of stellar atmospheres and convection, prompting advancements in computational modeling and observational techniques that can be applied to other distant, massive stars. Studying objects like UY Scuti also offers a benchmark for calibrating cosmic distance measurements. Its brightness and size, when accurately characterized, assist in refining the distance ladder, crucial for mapping the universe's expansion and understanding dark energy. Moreover, UY Scuti's sheer scale provides context to gauge the diversity of stellar phenomena across different galactic environments, enriching our grasp of how stars evolve under varying conditions. In essence, examining UY Scuti extends the frontiers of astrophysics and cosmology. It challenges existing theories, catalyzes technological innovation, and deepens our comprehension of the universe's most extreme objects. As we push to understand such giants, our knowledge of the cosmos becomes more nuanced, ultimately contributing to a more complete picture of the universe's origins, its ongoing evolution, and its ultimate fate. Observing UY Scuti from Earth presents a formidable set of technical challenges that stem from its extraordinary size and distance. While its sheer luminosity makes it an intriguing target, capturing detailed and accurate measurements requires overcoming numerous obstacles intrinsic to ground-based astronomy. One fundamental issue is the star's apparent brightness, which, despite its brilliance, still competes with atmospheric effects that distort incoming light. This distortion hampers high-resolution imaging and precise photometry, both essential for understanding the star's properties. Atmospheric turbulence, commonly known as seeing, causes the star's light to twinkle and blur as it passes through Earth's turbulent layers. This phenomenon limits the angular resolution achievable with ground-based telescopes, making it difficult to resolve the star's outer layers or detect subtle variations in its brightness. Adaptive optics systems have been developed to counteract this effect by dynamically adjusting telescope optics to compensate for atmospheric distortions. However, the effectiveness of these systems depends on the availability of bright guide stars or artificial laser beacons, which are not always feasible in the vicinity of UY Scuti. Another significant challenge is atmospheric absorption and scattering. Earth's atmosphere contains molecules and aerosols that absorb specific wavelengths of light, especially in the ultraviolet and infrared regions crucial for stellar analysis. This absorption reduces the clarity and intensity of the signals received, complicating spectroscopic observations that are vital for determining the star's composition, temperature, and velocity. Scattering further muddles the data by dispersing light in unpredictable ways, adding noise and reducing the signal-to-noise ratio. Timing also plays a role. Weather conditions such as clouds, humidity, and air pollution can abruptly interrupt observations or degrade data quality. For a star as distant and vast as UY Scuti, where minute details matter, these atmospheric limitations impose significant constraints on the precision and depth of ground-based study. Consequently, astronomers often turn to space-based observatories to bypass many of these atmospheric hurdles, aiming for clearer, more detailed insights into this colossal stellar entity. Earth's atmosphere, while a protective shield vital for sustaining life, imposes significant constraints on astronomical observations, especially when studying distant supergiant stars like UY Scuti. As light from these luminous giants travels across vast cosmic distances, it must pass through layers of atmospheric gases, which introduce distortions and scattering effects that degrade the clarity and precision of the data collected from ground-based telescopes. One of the primary atmospheric influences is turbulence, a phenomenon caused by temperature fluctuations and varying densities within different atmospheric layers. This turbulence causes the light waves to bend unpredictably, resulting in a phenomenon known as seeing. The effect manifests as a shimmering or blurring of celestial objects, making it exceedingly difficult to resolve fine details such as the star's surface features or subtle variations in brightness. For supergiants like UY Scuti, which already have complex and dynamic atmospheres, these distortions can obscure critical information about their structure and behavior. Additionally, atmospheric absorption plays a substantial role. Molecules like water vapor, oxygen, and carbon dioxide absorb specific wavelengths of electromagnetic radiation, particularly in the infrared and ultraviolet regions. This absorption limits the range of wavelengths that can be effectively observed from the ground, constraining our ability to analyze the star's spectrum comprehensively. As a result, essential spectral lines that reveal temperature, composition, and velocity fields may be partially or wholly obscured, complicating efforts to understand the physical processes occurring within these colossal stars. Weather conditions further compound these challenges. Cloud cover, humidity, and air pollution can temporarily or permanently hinder observations, reducing the amount of usable data and often requiring astronomers to wait prolonged periods for optimal conditions. This unpredictability hampers time-sensitive studies of variable stellar phenomena, which are common in supergiant stars with their ever-changing atmospheres. These atmospheric limitations underscore the need for alternative observational platforms. Space-based telescopes, freed from Earth's atmospheric distortions, open new horizons for detailed, high-resolution studies of distant stars like UY Scuti, allowing astronomers to peer into stellar surfaces and atmospheres with unprecedented clarity. Space telescopes have revolutionized our ability to study distant, colossal stars like UY Scuti by providing a vantage point free from Earth's atmospheric distortions. Earth's atmosphere, with its turbulence and absorption of certain wavelengths, imposes fundamental limitations on ground-based observations. Space telescopes circumvent these issues, capturing clearer, more precise data across a range of wavelengths, visible, infrared, and beyond, that are crucial for understanding the complex atmospheres and surface phenomena of supergiants. One of the key advantages of space-based observatories, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, lies in their ability to conduct high-resolution imaging for UY Scuti. This means resolving its extended atmosphere and detecting subtle brightness variations that might be smeared or obscured otherwise. Infrared capabilities in particular allow astronomers to peer through thick layers of dust and gas surrounding such stars, revealing details impossible to discern from the ground. Beyond imaging, space telescopes facilitate precise spectroscopic measurements. Spectroscopy provides insights into the star's composition, temperature, and velocity fields. Since supergiants like UY Scuti exhibit dynamic atmospheres with pulsations and mass loss episodes, high-quality spectroscopic data are essential for tracking these phenomena over time. The stability of space-based instruments ensures consistency in measurements, enabling long-term monitoring that captures the star's variability with minimal interference. Additionally, space telescopes play a vital role in time-domain astronomy, allowing continuous observation sequences that help identify transient events or periodic fluctuations. This persistent monitoring is critical for understanding the intrinsic variability of UY Scuti, which can be influenced by pulsations, convection cells, or other instabilities. While these instruments dramatically improve data quality, they are not immune to limitations. Variability in the star itself, measurement uncertainties, and instrumental calibration challenges persist. Addressing these issues requires sophisticated data analysis techniques, an area where space telescopes' stable and precise measurements serve as a foundational advantage. As we delve deeper into understanding UY Scuti's behavior, the synergy between advanced observational tools and analytical methods becomes increasingly vital. Astronomers employ a variety of sophisticated techniques to address the inherent variability and measurement uncertainties that complicate the study of UY Scuti. The stars fluctuates over time due to pulsations and other dynamic processes. Long-term, repeated observations essential. By monitoring UY Scuti across multiple wavelengths and over extended periods, astronomers can distinguish between intrinsic stellar variability and measurement noise. This approach helps in constructing more accurate light curves, which reveal the star's true luminosity patterns and facilitate refined size estimates. In addition, the use of statistical methods plays a crucial role in quantifying uncertainties. Techniques, such as Bayesian inference, allow researchers to incorporate prior knowledge and observational data, generating probability distributions for key parameters like radius and distance. These probabilistic models provide a clearer picture of the range within which the true values are likely to lie, acknowledging the limitations inherent in any single measurement. Interferometry has revolutionized stellar measurement, enabling astronomers to resolve the disk of UY Scuti with unprecedented precision. Yet, this technique is not immune to uncertainties stemming from atmospheric disturbances, calibration errors, and instrumental limitations. To mitigate these factors, astronomers often combine data from multiple interferometric observations, cross-validating results to improve reliability. Similarly, parallax measurements, used to determine distance, are subject to uncertainties due to the star's vast distance and the minute shifts involved. Space-based observatories such as Gaia have enhanced parallax accuracy, but confidence levels still depend on the star's brightness, position, and the quality of the data collected over time. Despite these advancements, the challenge remains to disentangle measurement errors from the star's intrinsic properties. Variability in brightness, coupled with the limitations of current technology, makes it difficult to pin down precise values. Consequently, astronomers must interpret data within the context of these uncertainties, often presenting a range of possible sizes and distances rather than definitive figures. This cautious approach underscores the complexities faced when studying some of the universe's most colossal stars. Despite considerable advancements in observational astronomy, accurately determining the size and distance of UY Scuti remains a formidable challenge due to inherent technological limitations. One primary obstacle is the immense distance separating us from the star, estimated to be around 9,500 light-years away. At such vast scales, even the most sophisticated telescopes struggle to resolve the star's disk directly. Instead, astronomers rely on indirect methods, such as analyzing brightness variations and spectral data, which introduce uncertainties. For example, deriving the star's radius often depends on interpreting its luminosity and temperature, but these parameters can be affected by interstellar dust, which dims and reddens the star's light, complicating precise calculations. Similarly, measuring the star's distance involves techniques like parallax, where tiny shifts in the star's apparent position against background stars are observed as Earth orbits the Sun. However, for objects beyond a few thousand light-years, these shifts become exceedingly small, fractions of a milliarc second, pushing the limits of current instrumentation. Even space-based observatories such as Gaia encounter difficulties in capturing such minute positional changes, especially when the star's brightness varies or when observational noise interferes. Furthermore, atmospheric disturbances inhibit ground-based telescopes from achieving the necessary resolution, forcing astronomers to depend heavily on space-based technologies or complex modeling. These models, while sophisticated, are only as accurate as the underlying assumptions and data allow. Variability in the star's brightness due to pulsations or stellar activity adds another layer of complexity, making it difficult to pin down a definitive size or distance. All these factors underscore a fundamental challenge: the reliance on indirect measurement techniques, which are inherently limited by the resolution and sensitivity of current instruments. As technology continues to evolve, developing methods to mitigate these limitations remains crucial for refining our understanding of stars like UY Scuti. This naturally leads to the question of how astronomers calibrate their instruments, ensuring the highest possible precision in their measurements of such distant and colossal objects. To accurately measure the immense and distant UY Scuti, astronomers rely on meticulous calibration processes that ensure their instruments produce reliable data. Calibration is essential because observational equipment, telescopes, detectors, and spectrometers are influenced by various factors such as temperature fluctuations, electronic noise, and atmospheric conditions. Without proper calibration, measurements of brightness, size, and distance could be significantly skewed, leading to erroneous conclusions about this colossal star. One foundational step involves using standard calibration sources, often stars with well-known properties. These standard stars serve as benchmarks. Astronomers compare their observations against established data to identify and correct any discrepancies in their instruments. For example, by observing a standard star with a precisely known brightness, they can calibrate the detector's response, ensuring subsequent measurements of UY Scuti are accurate. This process, called photometric calibration, accounts for atmospheric extinction, the dimming of starlight as it passes through Earth's atmosphere, by measuring how the atmosphere affects the observed flux. Spectroscopic calibration adds another layer of precision. It involves using emission lines from calibration lamps or known spectral features from standard stars to correct wavelength measurements. Precise wavelength calibration is crucial for determining the star's velocity and elemental composition. Additionally, flat field calibration ensures uniform sensitivity across the detector's surface, correcting for pixel-to-pixel variations that could distort measurements. Modern calibration techniques also incorporate adaptive optics systems which compensate for atmospheric turbulence in real time, sharpening the images and reducing measurement uncertainties. Calibration is an ongoing process. As instruments age or environmental conditions change, recalibration ensures continued accuracy. These rigorous calibration procedures form the backbone of reliable astronomical observations. They allow scientists to discern subtle features of UY Scuti's size, temperature, and luminosity, despite the challenges posed by its distance and the star's enormous scale. As observational technology advances, so too will the precision of these calibration methods, paving the way for even more detailed studies of such extraordinary celestial objects. Building on this foundation, the next frontier involves technological innovations that promise to revolutionize how we observe UY Scuti and similar stars, enhancing our understanding of their nature and evolution. Advancements in astronomical technology promise to significantly enhance our ability to observe and understand UY Scuti with greater clarity and depth. As current instruments reach their limitations, whether in resolution, sensitivity, or ability to penetrate Earth's atmosphere, next-generation telescopes and innovative observational techniques are poised to revolutionize our study of such colossal stars. The development of extremely large telescopes, ELTs, with primary mirrors spanning 30 meters or more, stands at the forefront of this progress. These colossal instruments, equipped with adaptive optics systems, will dramatically improve angular resolution, allowing astronomers to resolve finer details in the star's structure and surrounding environment that are currently blurred or indistinguishable. Another promising avenue involves space-based observatories designed to circumvent atmospheric distortions entirely. Instruments like the James Webb Space Telescope, JWST, with its powerful infrared capabilities, can peer through dust clouds and reveal aspects of UY Scuti that are obscured from ground-based observations. Future missions could incorporate even larger or more specialized infrared telescopes tailored to detect subtle features such as surface irregularities, pulsations, or mass loss phenomena characteristic of hypergiance. Advances in interferometry also hold great potential. Techniques combining the light collected by multiple telescopes across vast distances, very long baseline interferometry, VLBI, can achieve resolution far surpassing that of individual telescopes. As this technology matures and integrates more telescopic arrays, it could enable detailed imaging of the star's outer layers, shedding light on the complex processes of stellar convection and mass ejection. Complementing hardware improvements are innovations in detector sensitivity and data acquisition methods. The integration of cutting-edge sensors, such as superconducting detectors, will enhance our ability to capture faint signals with unprecedented precision. These detectors can operate across broader wavelength ranges, providing a more comprehensive picture of UY Scuti's dynamic atmosphere. Together, these technological advancements will not only refine our visual and spectral data, but also open new windows into the physical phenomena occurring in and around UY Scuti. As observational capabilities grow more sophisticated, they will set the stage for deeper insights into the life cycle of massive stars and their influence on galactic evolution. Data analysis and modeling serve as vital tools in deciphering the complex observations of UY Scuti, transforming raw data into meaningful insights about this colossal star. Given the star's extraordinary size and variability, astronomers rely on sophisticated techniques to interpret the wealth of information gathered through telescopic imaging and spectroscopy. High-precision photometric data, for example, reveal subtle fluctuations in brightness that can indicate pulsations or atmospheric changes. Analyzing these variations requires detailed statistical methods to distinguish genuine signals from noise, enabling researchers to track the star's behavior over time. Spectroscopic data further deepen understanding by providing insights into UY Scuti's surface composition, temperature gradients, and wind dynamics. Interpreting these spectra involves complex modeling to account for the star's extended, dynamic atmosphere, where molecules and ions interact under extreme conditions. Radiative transfer models simulate how light propagates through the star's layers, helping to estimate parameters like radius, mass loss rate, and surface gravity with greater accuracy. These models are continually refined through iterative comparisons with observational data, revealing the intricate interplay of physical processes, shaping UY Scuti's evolution. Moreover, computational simulations of stellar structure and evolution are indispensable for contextualizing observational findings within broader astrophysical theories. By inputting parameters derived from observations, models can predict the star's past and future development, including its stability and lifespan as a red supergiant. Such simulations also explore how internal processes like convection and nuclear fusion influence observable phenomena. The integration of data analysis and modeling thus creates a comprehensive picture that would be impossible to achieve through observations alone. This synergy between empirical data and theoretical frameworks not only enhances our understanding of UY Scuti's current state, but also guides the design of future observational strategies. As technology advances, these models will become increasingly precise, allowing astronomers to probe deeper into the star's mysteries. The ongoing refinement of analysis techniques paves the way for upcoming telescopes and missions to unlock even more secrets of this stellar giant. The future of UY Scuti research. As technological innovation continues to accelerate, a new wave of telescopes and space missions promises to deepen our understanding of colossal stars like UY Scuti. Among these, the James Webb Space Telescope, JWST, stands out as a transformative tool. Its unparalleled infrared sensitivity allows astronomers to peer through dense layers of dust and gas that often obscure supergiants, providing clearer insights into their atmospheres, surface phenomena, and mass loss processes. By capturing high-resolution spectra and detailed images, JWST can help disentangle the complex interactions within UY Scuti's extended envelope, revealing subtle variations in temperature, composition, and stellar winds that have eluded previous observations. Complementing JWST's capabilities, the European Space Agency's upcoming aerial mission aims to specialize in exoplanetary atmospheres, but also offers potential for studying stellar environments with its advanced spectrometers. While primarily designed for exoplanet research, Ariel's precise spectral analysis could be adapted to examine the chemical signatures and dynamic processes in supergiant stars, especially when combined with other observatories. Such data could shed light on how massive stars lose mass and evolve over time, processes critical to understanding their life cycles and ultimate fate. On the ground, the Extremely Large Telescope, ELT, currently under construction in Chile, promises to revolutionize stellar observations through its enormous aperture and adaptive optics systems. Its ability to resolve fine details on distant stellar surfaces will enable astronomers to observe surface granulation, star spots, and pulsations with unprecedented clarity. For a star as vast and complex as UY Scuti, the ELT could provide a spatially detailed map of its outer layers, offering insights into the mechanisms driving its variability and mass ejections. These cutting-edge instruments, each with unique strengths, are poised to transform supergiant star research. By capturing data across multiple wavelengths with greater precision, they will help unravel the intricate processes governing stars like UY Scuti, ultimately refining models of stellar evolution and challenging long-standing assumptions in astrophysics. Advancements in spectroscopy and imaging techniques stand poised to revolutionize our understanding of supergiant stars like UY Scuti. As technology progresses, astronomers can probe these colossal celestial bodies with unprecedented precision, unveiling details that were once beyond reach. High-resolution spectroscopy, for instance, allows scientists to analyze the star's light across a broad spectrum, revealing subtle shifts in absorption lines that correspond to elemental compositions, temperature fluctuations, and dynamic processes within the star's atmosphere. Such detailed insights can help refine models of stellar evolution, especially for stars on the brink of supernova stages, by clarifying how their outer layers behave and interact. Similarly, improvements in imaging, particularly interferometry and adaptive optics, are enabling astronomers to capture sharper, more detailed images of supergiant surfaces. These techniques can resolve surface features such as convective cells or star spots, which influence the star's brightness and spectral signatures. By mapping these features over time, researchers gain a deeper understanding of the turbulent processes driving mass loss and variability in stars like UY Scuti. As imaging resolution improves, scientists can also better measure the star's extended atmosphere and circumstellar environment, shedding light on how massive stars shed their outer layers and enrich the surrounding space. The integration of these advanced methods fosters a more comprehensive view of supergiant stars' complex atmospheres and internal dynamics. They also facilitate the detection of phenomena such as pulsations, magnetic activity, or even unseen companions, which could significantly influence the star's evolution. As computational power and data analysis techniques continue to advance, the ability to interpret vast datasets from spectroscopic and imaging observations will become increasingly sophisticated, revealing nuances in stellar behavior. Ultimately, These technological strides promise a deeper, more nuanced understanding of UY Scuti's life cycle, its influence on the galactic environment, and the fundamental processes governing the most massive stars. Each breakthrough brings us closer to unraveling the mysteries of these cosmic giants, laying the groundwork for discoveries that could reshape our conception of stellar evolution and the extreme environments within our universe. Future research into UY Scuti promises to unlock a wealth of insights that could deepen our understanding of the most massive stars in the universe. One compelling avenue involves refining measurements of its physical parameters, such as its exact size, mass, and surface temperature. As observational technologies improve, astronomers may obtain more precise data that reveal subtle variations in these parameters over time. Such variations could shed light on the star's internal processes, including pulsations and mass loss mechanisms, which play crucial roles in its life cycle. Additionally, enhanced spectroscopic studies might uncover details about UY Scuti's chemical composition, revealing how nuclear fusion and convection distribute elements within the star. These insights could challenge or confirm current models of stellar evolution at the upper mass limits, especially regarding how supergiants shed their outer layers. Understanding the composition and dynamics of these layers can also inform predictions about when and how UY Scuti might end its life, whether in a supernova, a neutron star, or a black hole. Advances in high-resolution imaging and interferometry could also enable astronomers to observe surface phenomena directly. Detecting large-scale convection cells, star spots, or pulsation modes would provide clues about the star's internal structure and energy transport mechanisms. Such observations might reveal asymmetries or irregularities that influence mass loss and evolution, offering a more nuanced picture than current models allow. Another promising frontier involves studying the star's immediate environment, its stellar wind, and any circumstellar material. Future telescopes could trace the outflows of gas and dust in unprecedented detail, helping to clarify how supergiants like UY Scuti contribute to the enrichment of the interstellar medium. Ultimately, these discoveries will not only refine our understanding of UY Scuti itself, but also have broader implications for astrophysics. They could illuminate the life cycles of the most massive stars, influence models of galaxy evolution, and enhance our comprehension of the cosmic processes that shape the universe. As observational and computational capabilities continue to advance, the potential for groundbreaking revelations about this colossal star remains vast. Advancements in computational modeling stand at the forefront of deepening our understanding of supergiant star evolution, including enigmatic giants like UY Scuti. These models serve as virtual laboratories, allowing astronomers to simulate the complex physical processes occurring within such colossal stars, processes that are often impossible to observe directly due to their vast distances and extended lifespans. By incorporating refined physics, such as convection, radiation transfer, nuclear fusion, and mass loss mechanisms, computational models can generate more accurate predictions of a star's life cycle, internal structure, and eventual fate. Recent progress in high-performance computing has enabled simulations that capture the dynamism of supergiants with unprecedented detail. For instance, three-dimensional models now account for turbulent convection zones and asymmetric mass ejections, phenomena critical to understanding how these stars shed their outer layers. These simulations help clarify how variations in metallicity, rotation, and magnetic fields influence a star's evolution, enriching our theoretical frameworks. As models become more sophisticated, they can also incorporate observational data from telescopes and interferometers, leading to tighter constraints and validation of theoretical predictions. Refining these models further enhances our comprehension of the processes that govern the lifespan of stars like UY Scuti, including how they grow so enormous, how they maintain stability amidst turbulent internal conditions, and what triggers the final stages of their evolution. Improved computational approaches also shed light on the precursors to supernova explosions and the formation of neutron stars or black holes, phenomena linked to the ultimate demise of supergiants. As the complexity of these models increases, their predictive power improves, offering insights that guide future observations. They help identify key signatures to look for in spectral data or variability patterns, effectively turning simulations into tools for hypothesis testing. In this way, enhanced computational modeling acts as a bridge between theory and observation, continually refining our picture of how supergiants like UY Scuti develop and evolve over cosmic timescales. Building on these advances, the role of international collaborations becomes paramount, combining resources, expertise, and observational data from around the world to push the frontiers of stellar astrophysics even further. International collaborations are poised to be instrumental in unlocking the mysteries of UY Scuti, given the star's extraordinary size and the scientific challenges it presents. The sheer scale of UY Scuti demands a concerted effort that spans multiple disciplines, institutions, and countries. By pooling resources, such as advanced telescopes, cutting-edge computational models, and specialized expertise, research teams can push the boundaries of what is currently possible in stellar observation and analysis. Large-scale projects, like the European Southern Observatory's Very Large Telescope, VLT, and the upcoming James Webb Space Telescope, exemplify how shared infrastructure can significantly enhance our ability to study distant, massive stars. Combining data from different observatories around the globe allows astronomers to obtain high-resolution images, precise measurements, and detailed spectra that would be difficult or impossible to achieve individually. These collaborations also facilitate the development of standardized methodologies, enabling consistent data collection and interpretation across different research groups. International partnerships foster the exchange of knowledge and technological innovation. For example, advances in adaptive optics, originally developed for terrestrial telescopes, have been refined through cross-border cooperation, allowing astronomers to correct atmospheric distortions and improve the clarity of observations. Such technological improvements are crucial when attempting to measure the subtle features of a star as distant and luminous as UY Scuti. Furthermore, collaborative efforts open avenues for large-scale data analysis, employing machine learning algorithms and artificial intelligence to process the enormous datasets generated. This collective approach accelerates discovery and helps to identify patterns or anomalies that might otherwise be overlooked. By uniting the global scientific community, research into UY Scuti transcends individual limitations, paving the way for breakthroughs in understanding massive stellar evolution, the life cycles of supergiants, and the broader mechanisms shaping our universe. These partnerships ultimately not only deepen our grasp of this singular star, but also set a precedent for investigating other cosmic giants, enriching our comprehension of the universe's vast and intricate structure. Studying UY Scuti offers profound implications for refining our grasp of the universe's vastness and its overarching architecture. As one of the largest known stars, UY Scuti acts as a benchmark for understanding the upper limits of stellar size and mass, prompting astronomers to reconsider the boundaries of stellar evolution. Its sheer scale challenges existing models, compelling scientists to explore the physical processes that allow such enormous stars to form and persist without collapsing under their own gravity or dispersing due to energetic winds. The insights gleaned from UY Scuti's structure and behavior extend beyond stellar physics, influencing our perception of cosmic scale. Precise measurements of its dimensions serve to calibrate the methods used to estimate distances and sizes of other celestial objects, especially in the realm of supergiants and variable stars. These calibrations, in turn, enhance the accuracy of distance ladders, tools fundamental to mapping the universe's expansion and understanding its large-scale structure. As UY Scuti's characteristics become clearer, they help refine models of galaxy formation, since such colossal stars often reside in dense stellar environments that shape galactic evolution. Moreover, studying UY Scuti deepens our comprehension of the life cycles of massive stars, revealing how they influence their surroundings through intense radiation, stellar winds, and eventual supernova explosions. These processes contribute to the enrichment of the interstellar medium, fostering star formation in neighboring regions. Understanding these feedback mechanisms allows us to better grasp how galaxies evolve over cosmic timescales, linking the fate of individual stars to the broader narrative of the universe's development. Ultimately, UY Scuti acts as a cosmic yardstick, both literally and figuratively, pushing the boundaries of our scientific understanding. Its study encourages a re-evaluation of the extremes of stellar and galactic phenomena, prompting questions about the processes that govern the universe's structure on its grandest scales. As new observational technologies emerge, the potential to unravel more about such giants promises to reshape our cosmic perspective significantly. Observing UY Scuti in the coming decades presents both notable challenges and promising opportunities that could significantly advance our understanding of the universe's most colossal stars. One primary challenge lies in the star's inherent variability and its vast distance from Earth. Its size and brightness fluctuate over time, making precise measurements a moving target and complicating efforts to track its evolution accurately. Additionally, the star's extensive size results in a complex atmosphere riddled with turbulent convection zones, which can obscure direct observation and limit the resolution of current telescopic technologies. The limitations of existing observational instruments also pose hurdles. Although advancements in adaptive optics, interferometry, and space-based telescopes have improved our capacity to study such distant giants, resolving the fine details of UY Scuti's outer layers remains difficult. As technology progresses, however, opportunities emerge. Next-generation telescopes, such as the Extremely Large Telescope, ELT, and the James Webb Space Telescope, JWST, promise unprecedented sensitivity and resolution, enabling astronomers to probe deeper into the star's structure and monitor its behavior with greater precision. Long-term monitoring campaigns offer valuable prospects for understanding the life cycle of hypergiants like UY Scuti. Continuous observation can reveal changes in brightness, surface activity, and mass loss rates, shedding light on the final stages of stellar evolution for the most massive stars. Importantly, these insights could refine models of supernova progenitors, influencing our grasp of how such cosmic behemoths end their lives and seed the universe with heavy elements. While technical and environmental challenges are formidable, they are matched by a rich landscape of scientific opportunity. Each incremental improvement in observational capability not only enhances our knowledge of UY Scuti itself, but also deepens our comprehension of stellar physics at the extreme end of the scale. This ongoing pursuit exemplifies humanity's enduring quest to unveil the universe's most awe-inspiring phenomena and paves the way for discoveries that could reshape our understanding of stellar life cycles and cosmic evolution. Public engagement and education surrounding UY Scuti serve as vital bridges between the scientific community and the broader public, fostering curiosity and a deeper appreciation for the complexities of stellar phenomena. As ongoing research continues to unravel the mysteries of this colossal star, translating these findings into accessible narratives can inspire future generations of scientists and ignite public interest in astronomy. Visual aids, such as detailed models and striking images, help convey the star's enormity and unique characteristics, making abstract concepts tangible for diverse audiences. Explaining the significance of UY Scuti's size and behavior can also illuminate fundamental astrophysical principles, such as stellar evolution and the life cycle of massive stars, thereby enriching science literacy. Educational outreach programs that incorporate the latest discoveries about UY Scuti can stimulate interactive learning experiences. For instance, citizen science projects might invite enthusiasts to assist in analyzing data or participate in simulations, fostering a sense of involvement and ownership in scientific progress. Such initiatives can demystify complex research techniques and highlight how technological advancements, like high-resolution telescopes and computational modeling, are pivotal in expanding our understanding of the universe. These activities not only make science more accessible, but also demonstrate its dynamic, collaborative nature. Public engagement also plays a crucial role in shaping perceptions of astronomy's relevance to societal challenges, emphasizing the importance of continued investment in space research. By showcasing how studying supergiants like UY Scuti informs models of stellar evolution, supernova mechanisms, and cosmic distance measurement, scientists can underscore the broader impact of astrophysics on our comprehension of the universe. Additionally, storytelling that humanizes the quest to understand objects of such magnitude can foster a sense of wonder and shared curiosity. As research progresses, the storytelling surrounding UY Scuti can evolve, incorporating new discoveries into educational content and outreach efforts. The ongoing fascination with this stellar giant offers a unique opportunity to engage diverse audiences, inspire scientific pursuits, and elevate public understanding of the universe's grand scale. Such efforts ensure that the quest to comprehend stars like UY Scuti remains a collective endeavor, energizing both scientific inquiry and societal appreciation of our cosmic neighborhood. Understanding the complex structure and behavior of UY Scuti relies heavily on sophisticated theoretical models that blend physics, astronomy, and computational science. These models serve as virtual laboratories, allowing scientists to explore the internal processes and evolutionary pathways of such colossal stars with an accuracy impossible through observation alone. Central to this effort are stellar evolution codes, comprehensive simulation tools that incorporate the principles of nuclear physics, fluid dynamics, thermodynamics, and radiative transfer. One of the primary frameworks used is the Hennier-type stellar evolution code, which tracks a star's life cycle from its formation through various stages of fusion and expansion. These models start with initial conditions, mass, composition, and rotation, and simulate how internal temperatures, pressures, densities evolve over time. They incorporate detailed nuclear reaction networks to model fusion processes, particularly the fusion of hydrogen into helium in the core and subsequent heavier element fusion in later stages. These codes also account for mass loss phenomena, such as stellar winds, which are especially significant in supergiants like UY Scuti due to their intense outflows. Another crucial element in modeling UY Scuti involves the treatment of convection and turbulence within the star's vast outer layers. Convection models help predict how energy is transported from the core to the surface, influencing surface temperature, luminosity, and radius. Because supergiants exhibit complex, turbulent atmospheres, multidimensional hydrodynamic simulations are increasingly employed to capture the nuanced behavior of stellar convection, pulsations, and instabilities that impact their evolution. Magnetic field effects and rotation are also integrated into advanced models, as both significantly influence angular momentum distribution, mass loss rates, and surface phenomena. These comprehensive simulations are continually refined by comparing their predictions with observational data, such as brightness variations and spectral signatures. Collectively, these theoretical models form the backbone of our understanding of supergiant stars like UY Scuti. They enable astronomers to not only interpret the star's current state, but also project its possible future evolution, setting the stage for the next frontier. How computational simulations can forecast the destiny of these cosmic giants. Computer simulations serve as vital tools for unraveling the complex future of supergiant stars like UY Scuti. These models integrate fundamental physical principles to project how such enormous stars evolve over millions of years, providing insights that are impossible to observe directly due to their lengthy lifespans. At their core, these simulations aim to replicate the intricate interplay of processes, nuclear fusion, convection, mass loss, and changes in stellar structure that dictate a star's trajectory toward its ultimate fate. One of the primary advantages of computational modeling lies in its ability to explore various scenarios by adjusting initial conditions and physical parameters. For UY Scuti, models incorporate detailed physics to simulate its current state, including its large radius, luminosity, and surface temperature. These parameters influence how energy is transported within the star, affecting fusion rates and the star's overall stability. By iterating these models over time, astrophysicists can predict when UY Scuti might exhaust its nuclear fuel, transition into later evolutionary phases, or shed significant portions of its mass through stellar winds. Mass loss plays a pivotal role in shaping the star's future, and simulations strive to accurately depict this process. They account for the complex physics of stellar winds, driven by radiation pressure, pulsations, and magnetic fields, and how this mass ejection influences the star's structure and luminosity. As mass diminishes, models can forecast whether UY Scuti will contract into a more compact supernova progenitor or evolve into a different stellar remnant. Simulations also incorporate the star's internal composition, including chemical abundances and stratification, which affect fusion pathways and energy generation. These internal characteristics determine how the star's core contracts or expands and influence its transition through various evolutionary stages. Ultimately, these computational tools serve as virtual laboratories, enabling scientists to probe the life cycle of supergiants like UY Scuti. They provide not only a glimpse into the star's possible futures, but also deepen our understanding of the physical laws governing stellar evolution at the most colossal scales. To accurately simulate the behavior of a star as immense and complex as UY Scuti, models must incorporate a comprehensive suite of physical parameters that capture its internal and external dynamics. Central among these are the star's mass, radius, and luminosity, which serve as foundational inputs, influencing the overall energy output and structure. These parameters are intertwined with the star's temperature profile, both at the core and across its extensive surface layers, dictating fusion rates and the nature of energy transport within the stellar interior. A critical consideration in modeling UY Scuti involves the density distribution throughout its expansive envelope. Given its status as a red supergiant, the star exhibits a highly stratified atmosphere with significant variations in density and pressure. Capturing these gradients requires detailed equations of state that account for ionization, molecular formation, and partial degeneracy effects. Additionally, the models incorporate opacity sources, such as absorption by molecules like water vapor and titanium oxide, that profoundly influence radiative transfer and surface temperature structures. The dynamics of convective energy transport are especially vital in describing UY Scuti's outer layers. Convection zones dominate this region, necessitating parameters that characterize convective velocities, mixing lengths, and turbulence. These parameters help simulate the large-scale convective cells responsible for surface granulation and variability, phenomena observed in red supergiants. To account for the star's substantial mass loss via stellar winds, models include parameters governing wind velocity profiles, mass loss rates, and the influence of radiation pressure on dust and gas particles. Magnetic fields, though less directly measurable, are also integrated into sophisticated models, as they can influence surface activity and wind dynamics. Overall, creating a realistic representation of UY Scuti demands a delicate balance of these parameters, each rooted in fundamental physics, yet tailored to reflect the star's unique and extreme environment. This detailed parameter set forms the backbone of simulations that strive to unravel the complex processes shaping such a colossal stellar entity. Modeling the intricate phenomena of stellar winds and surface convection presents one of the most formidable challenges in astrophysics. For stars like UY Scuti, whose immense size and complex outer layers defy simplistic descriptions, capturing these processes requires sophisticated approaches that blend physics, computational techniques, and observational constraints. Stellar winds, continuous flows of particles driven from the star's surface, are primarily influenced by a combination of radiation pressure, magnetic fields, and thermal gradients. To simulate these, models incorporate hydrodynamic equations that describe how plasma accelerates outward, often employing multidimensional magnetohydrodynamic (MHD) codes. These codes account for the star's intense radiation, which imparts momentum to the outer layers, as well as magnetic field interactions that can channel and intensify wind flows. Yet, the coupling between radiative transfer and fluid dynamics involves complex feedback mechanisms, making precise modeling computationally demanding. Surface convection, responsible for the turbulent granulation patterns observed on red supergiants like UY Scuti, adds another layer of complexity. Convection involves the movement of plasma driven by buoyancy differences, transporting energy from the interior toward the surface. Capturing this process necessitates high-resolution 3D radiation hydrodynamic simulations that resolve convective cells spanning vast scales. These models must incorporate detailed opacity data, radiative transfer, and magnetic influences, all of which shape the convective behavior. Given the star's enormous size and the turbulent nature of convection, simulations often rely on approximations and parameterizations to make computations feasible. Despite these advances, accurately representing such phenomena remains challenging. The interplay of magnetic fields, turbulence, and radiative forces occurs across a wide range of scales, many of which are below current computational resolution. Consequently, models often depend on simplified assumptions or empirical calibrations derived from observations. As a result, while simulations provide invaluable insights into stellar wind and convection dynamics, they are inherently limited by the complexity of the physics involved and the current state of computational technology. Despite the remarkable advances in computational astrophysics, current stellar models of stars like UY Scuti face significant limitations and uncertainties that challenge their precision and predictive power. These models rely heavily on complex physics, nuclear fusion, convection, radiation transfer, mass loss, and magnetic activity, all of which are inherently difficult to quantify with absolute certainty. For instance, convection processes within such enormous stars operate on scales that are impossible to resolve directly, necessitating the use of approximate methods like mixing length theory, which introduces uncertainties in energy transport predictions. Another key challenge involves modeling mass loss, a critical factor in the evolution of red supergiants. The mechanisms driving stellar winds in these stars are not fully understood, and the rates can vary widely due to pulsations, magnetic activity, or surface phenomena, making it difficult to accurately simulate their future evolution. Moreover, the composition and opacity of the stellar atmosphere influence radiative transfer. Yet, these parameters often depend on assumptions about metallicity and dust formation, which are not always well constrained observationally. Uncertainties also stem from the initial conditions fed into models, such as the star's mass, rotation rate, and magnetic field strength. Small variations in these parameters can lead to divergent evolutionary paths, especially over millions of years. Additionally, the complexity of UY Scuti's extended atmosphere and circumstellar environment often exceeds the resolution of current simulations, limiting the accuracy of models that aim to replicate its observable features. While stellar evolution codes incorporate sophisticated physics, their reliance on simplified physics and uncertain parameters underscore the importance of continuous refinement. These limitations highlight the need for a cautious interpretation of model predictions, emphasizing that they serve as approximations rather than definitive representations. As our understanding of stellar physics deepens and computational techniques improve, models will increasingly become tools that complement observational data, each informing and constraining the other to paint a more accurate picture of stars like UY Scuti. Simulations serve as a vital tool in bridging the gap between theoretical models and observational data for stars like UY Scuti. By constructing detailed computational models that incorporate known physics, such as nuclear fusion, stellar convection, radiation transport, and mass loss mechanisms, researchers can generate predictions about the star's behavior and structure. These models are then rigorously compared with observational indicators, including brightness variations, spectral signatures, and surface phenomena, to assess their accuracy and refine underlying assumptions. One key aspect of this comparison lies in the star's pulsation patterns. UY Scuti exhibits semi-regular variability, believed to stem from pulsations in its extended outer layers. Simulations that incorporate hydrodynamic equations and opacity variations can predict these pulsation modes and their amplitudes. When observational data align with these predictions, confidence in the models increases, confirming our understanding of the physical processes at play. Discrepancies, however, point to gaps, perhaps in the treatment of convection or mass loss rates, that require further refinement. Spectroscopic observations provide another critical benchmark. Simulations forecasting the star's surface temperature, chemical composition, and wind velocities can be validated against spectral lines observed through telescopes. For UY Scuti, matching the predicted mass loss rates and surface compositions with spectral data helps verify the accuracy of models describing its evolutionary stage and mass loss mechanisms. Consistency across these parameters supports the broader theories of red supergiant evolution and contributes to more precise estimates of the star's future trajectory. Advancements in computational power have allowed for increasingly sophisticated simulations that incorporate three-dimensional dynamics and turbulence, offering a more nuanced view of the star's interior and surface phenomena. These detailed models, when correlated with high-resolution observational data, not only validate existing theories, but also uncover subtle effects that might influence the star's evolution. As observational technology continues to improve, especially with upcoming telescopes capable of more detailed imaging, the iterative process of simulation and observation promises to deepen our understanding of giants like UY Scuti and the complex stellar processes they exemplify. This ongoing dialogue between models and datasets, the stage for exploring how such refined simulations can help us better anticipate the final stages of supergiants, including potential supernova precursors like UY Scuti. Modeling serves as an indispensable tool for unraveling the complex pre-supernova stages of colossal stars like UY Scuti. These simulations enable astrophysicists to delve into the intricate interplay of physical processes that precede such cataclysmic events. For instance, by constructing detailed models of UY Scuti's internal structure and evolution, researchers can better understand the conditions that lead to core instability, a critical precursor to supernova explosions. These models incorporate variables such as temperature gradients, nuclear fusion rates, and the behavior of turbulent convection within the star's expansive envelope, providing insights impossible to obtain solely through observation. One of the key advantages of advanced modeling lies in its ability to track the star's mass loss history. UY Scuti, like other red supergiants, sheds enormous amounts of material through stellar winds, forming complex circumstellar environments. Simulations that integrate these mass loss processes reveal how the star's outer layers evolve over time and influence its eventual fate. By capturing the dynamics of dust formation and the interactions between stellar winds and surrounding gas, models can predict how these factors might affect the star's stability and its proximity to supernova ignition. Furthermore, modeling offers a platform to explore multi-physics scenarios that encompass the effects of rotation, magnetic fields, and binarity, all of which can dramatically alter a star's evolutionary pathway. For UY Scuti, understanding whether such factors induce asymmetries or instabilities in its outer layers could clarify the timing and nature of the impending core collapse. These simulations also help interpret observational data, such as irregular brightness variations and spectral features, by linking them to internal stellar processes. As our computational capabilities expand, so too does the potential for more nuanced and precise models. Integrating high-resolution simulations with observational constraints will refine predictions about supernova precursors like UY Scuti, ultimately bringing us closer to identifying the exact signs that herald the star's imminent demise. Advancements in computational astrophysics continually push the boundaries of our understanding, and future developments promise to dramatically enhance the precision of stellar modeling, especially for colossal stars like UY Scuti. Central to these improvements are the increasing capabilities of high-performance computing (HPC) systems, which will enable simulations of unprecedented complexity and scale. As hardware accelerates, models can incorporate finer spatial and temporal resolutions, capturing subtle physical processes that previously remained elusive. One promising avenue involves the integration of more sophisticated physics into simulations. This includes detailed radiative transfer models that accurately depict how energy moves through the star's dense outer layers, as well as improved treatment of convection, turbulence, and magnetic fields. Magnetic phenomena, in particular, play a significant role in mass loss and angular momentum redistribution, yet they are notoriously challenging to model. Incorporating magnetohydrodynamics, MHD, with higher fidelity could unveil new insights into the star's stability and evolution. Machine learning, ML, and artificial intelligence, AI, also stand poised to revolutionize modeling techniques. These tools can analyze vast datasets from observations and simulations, identifying patterns and correlations that might escape traditional analysis. By training ML algorithms on a diverse array of stellar models, researchers can develop predictive frameworks that rapidly evaluate different evolutionary scenarios, refining parameters for future simulations. Moreover, the development of adaptive mesh refinement, AMR, techniques allows models to dynamically allocate computational resources to regions with complex physics or steep gradients, such as shock fronts or convective zones. This ensures higher accuracy where it matters most, without prohibitive computational costs. Lastly, collaborative efforts among international research communities will likely foster shared databases of observational data, physical constants, and simulation results. Such repositories will enable cross-validation and calibration of models, reducing uncertainties and leading to more reliable predictions. In essence, the convergence of hardware innovation, sophisticated physics, AI integration, and collaborative data sharing promises an era where the modeling of titanic stars like UY Scuti becomes increasingly precise, illuminating their intricate lives and ultimate destinies with unprecedented clarity. The ultimate destiny of a star, as colossal as UY Scuti, hinges on its core processes and the complex interplay of mass, energy, and nuclear reactions. Unlike smaller stars that gently fade into white dwarfs, red supergiants like UY Scuti face more dramatic finales, dictated by their immense size and energetic behaviors. As UY Scuti exhausts the nuclear fuel in its core, it transitions through a series of increasingly unstable phases that set the stage for its final act. One plausible scenario is that UY Scuti will undergo a core collapse supernova. In its later stages, the core's fusion processes will cease to support the outer layers, which are held aloft by radiative pressure. When the core's mass exceeds the Chandrasekhar limit, it becomes unable to resist gravitational collapse. This collapse would be rapid, compressing the core into a neutron star or, if the mass is sufficient, a black hole. The infall would generate an enormous release of energy, driving a shockwave outward that expels the star's outer layers in a cataclysmic explosion, a supernova. Alternatively, if UY Scuti's mass is just below the threshold for a supernova, it may shed its outer layers more gradually through intense stellar winds. Over thousands or even millions of years, the star would lose a significant portion of its mass, exposing its core and eventually ending as a dense, hot stellar remnant, likely a neutron star or black hole. This process would be less violent but still dramatic, as the star's outer envelope disperses into space, enriching the surrounding interstellar medium with heavy elements. Another intriguing possibility involves the star's instability, leading to episodic mass ejections, akin to luminous blue variables, though this is less likely given its evolutionary stage. Regardless of the pathway, the end of UY Scuti's life marks a profound transformation, leaving behind remnants that continue to influence their cosmic neighborhood. The question of whether UY Scuti will become a supernova remains open, but understanding these scenarios helps illuminate the final, spectacular chapters in the life of such a titanic star. UY Scuti's immense size and advanced evolutionary stage raise intriguing questions about its ultimate fate, particularly whether it could become a supernova. Unlike the smaller stars that explode in spectacular outbursts, UY Scuti's future hinges on the intricate balance of its core processes and mass loss over time. As a red supergiant, UY Scuti has already undergone significant fusion activities, converting hydrogen into helium and then heavier elements in its core. Its vast outer layers, however, are tenuously held by the star's gravity, making it prone to substantial mass ejections. These episodes of intense mass loss gradually peel away the star's outer envelope, exposing its core and altering its internal composition. For a star to explode as a supernova, it must reach a critical point where its core is composed of inert elements, typically iron, unable to produce energy through fusion. Iron accumulation occurs when the star's fusion processes produce increasingly heavier elements until iron is formed, which acts as a sort of energy sink rather than a source. Once the core becomes predominantly iron, it can no longer support the star's outer layers. In the case of UY Scuti, its mass is likely near the threshold where a supernova is possible, but not guaranteed. If it retains enough mass and the core reaches the critical iron stage, gravitational collapse could trigger a core collapse supernova, releasing enormous energy and dispersing its outer layers into space. This cataclysm would be one of the most luminous events observable across the galaxy, briefly outshining entire star clusters. Alternatively, if UY Scuti loses too much mass before reaching this stage, its core may not be massive enough to collapse violently. Instead, it could end its life quietly, shedding its outer layers to form a planetary nebula, leaving behind a dense core, either a neutron star or, in the case of a sufficiently massive remnant, a black hole. The precise outcome hinges on complex factors, including the star's mass, composition, and the dynamics of its late-stage fusion processes, making UY Scuti a spectacular yet unpredictable cosmic giant. As UY Scuti approaches the final chapters of its stellar journey, the remnants it leaves behind will be shaped significantly by its mass and the complex processes it undergoes during its death throes. Given its initial mass, estimated to be over 20 times that of our Sun, its ultimate fate will likely fall into one of two primary scenarios, either transforming into a neutron star or collapsing directly into a black hole. In the later stages of its evolution, UY Scuti will experience intense mass loss driven by powerful stellar winds and possibly episodic eruptions. These phenomena strip away the star's outer layers, reducing its overall mass and altering the dynamics of its core collapse. If enough mass is shed, the core's remaining mass may fall below the critical threshold needed to form a black hole, leading instead to the birth of a dense, neutron-rich remnant. Such a neutron star would be an incredibly compact object, roughly 20 kilometers in diameter, possessing a density so extreme that a single teaspoon of its material would weigh billions of tons. Conversely, if UY Scuti retains a substantial portion of its core mass despite its mass loss, the gravitational collapse could be so intense that it overcomes neutron degeneracy pressure, causing the star to form a black hole. This process is more probable if the star's initial mass is sufficiently high or if mass loss is insufficient to prevent the core from reaching the critical threshold. The formation of a black hole would mark a dramatic end, leaving behind a region of space-time where gravity is so overwhelming that not even light can escape. The nature of the remnant also depends on the intricacies of the star's internal composition and the complex physics governing supernova explosions. If UY Scuti undergoes a supernova, the explosion itself could influence the remnant's characteristics, dispersing some material into space and enriching the cosmic environment. Ultimately, whether UY Scuti leaves behind a neutron star or a black hole hinges on a delicate interplay between its initial mass, the extent of its mass loss, and the physics of core collapse, factors that will determine its final imprint on the universe. As UY Scuti approaches the final chapters of its stellar journey, the ongoing mass loss during its late stages plays a pivotal role in shaping its ultimate destiny. During the red supergiant phase, the star's expansive outer layers become increasingly unstable, leading to vigorous stellar winds that strip away vast amounts of material. This process is driven by complex interactions between radiation pressure, convection currents, and pulsations within the star's extended atmosphere. The shedding of mass is not a gentle drift, but a turbulent, episodic phenomenon that can result in the ejection of dense shells of gas and dust into space. This substantial loss of material profoundly influences the star's future evolution. As UY Scuti relinquishes its outer layers, its core is left exposed, increasing in temperature and density. The diminishing envelope means the star's outer radius contracts slightly, though it remains enormous by human standards. The decreasing mass also affects the star's internal fusion processes. With less gravitational pressure, the core's ongoing fusion reactions may weaken or alter, impacting the star's stability. Crucially, the amount and rate of mass loss determine whether UY Scuti will end its life as a neutron star or a black hole. If the star retains enough mass until the core collapse, it could produce a supernova explosion, dispersing heavy elements into the surrounding space and leaving behind a compact remnant. Conversely, if the mass loss reduces the core's mass below a critical threshold, the star might undergo a different evolutionary path, perhaps collapsing directly into a black hole with minimal explosive display. The dynamics of mass loss also influence the nature of the eventual supernova event itself. A star with significant mass loss might generate a different explosion signature compared to one that retains more of its initial mass. This ongoing shedding not only dictates the star's fate, but also enriches the cosmos with elements essential for planet formation and life. In essence, the star's final act hinges on how effectively it can offload its outer layers before the core's gravitational collapse, setting the stage for a spectacular cosmic finale. As UY Scuti approaches the culmination of its life cycle, several subtle yet telling signs emerge within its observable behavior and structure. Unlike the dramatic supernova explosions that mark the final act of some massive stars, red supergiants like UY Scuti typically exhibit warning signs during their late evolutionary stages that can be detected through careful monitoring. One of the primary indicators is an increase in mass loss rate. As the star exhausts its nuclear fuel, its outer layers become increasingly unstable, leading to enhanced stellar winds that eject material into space. This mass loss often manifests as a thickening of the circumstellar envelope, which can be detected through infrared observations, revealing excess thermal emission from dust and gas. A notable increase in variability or irregularities in brightness may accompany this phase, caused by pulsations deep within the star's extended atmosphere. These pulsations can become more pronounced, with fluctuations occurring over days or weeks, signaling internal structural changes. Spectroscopic analysis offers additional insights. Shifts in spectral lines, especially those associated with elements like hydrogen and helium, can indicate changes in the star's atmospheric composition and dynamics. Outward-moving layers may show Doppler shifts, revealing accelerated expansion indicative of impending instability. Furthermore, the star's radius might exhibit measurable expansion or contraction patterns, reflecting the complex interplay of fusion cessation and core contraction. On a more subtle level, astronomers observe shifts in surface temperature and luminosity. As the core contracts, the outer layers may cool or heat irregularly, producing observable variations in spectral energy distribution. These signs, combined with increased mass loss and pulsation activity, serve as the star's final warning signals that it is nearing its core collapse phase. Ultimately, while the processes happen gradually over centuries, advancements in high-resolution telescopes and spectroscopy enable astronomers to detect these precursors. Recognizing these signs allows scientists to piece together the star's final evolutionary steps, offering a rare glimpse into the dramatic transformation of one of the universe's most colossal stars. Predicting the precise timing of UY Scuti's transition into its final evolutionary phase presents a formidable challenge, owing to the complex and often unpredictable nature of massive stellar life cycles. Unlike more stable stars, supergiants like UY Scuti exhibit significant variability in their observable characteristics, such as brightness, size, and surface activity that can obscure clear evolutionary signals. To estimate when UY Scuti might reach the critical point of core collapse, astronomers rely on a combination of observational data, theoretical models, and an understanding of stellar physics. One key approach involves monitoring changes in the star's luminosity and spectral features over extended periods. Variations in brightness can indicate shifts in the star's internal processes, such as instabilities in the fusion reactions occurring within its core. Spectroscopic analysis reveals changes in surface composition and temperature, which can hint at internal structural transformations. For example, an increase in mass loss rates or surface turbulence may precede the final collapse, prompting astronomers to scrutinize these signals carefully. Complementing observational efforts are advanced computer models of stellar evolution. These models incorporate physical principles governing nuclear fusion, convection, and mass loss, allowing scientists to simulate UY Scuti's future trajectory based on its current parameters, mass, composition, and internal structure. By inputting real-time data into these models, researchers can estimate the star's remaining lifespan and identify potential markers of imminent transition, such as a rapid increase in core density or core temperature. Despite these tools, inherent uncertainties remain. The exact timing depends on factors like the star's precise mass, the rate of mass loss, and the behavior of its core, variables that are difficult to measure directly. As a result, predictions are probabilistic rather than definitive, often expressed as a range of possible years or decades. Continuous observation, coupled with refined models, remains essential to narrowing this window and understanding the impending finale of this colossal celestial entity. A supernova explosion of UY Scuti would cast profound effects across its surrounding environment, illustrating the dramatic culmination of its evolutionary journey. As a red supergiant nearing the end of its life, UY Scuti's core would eventually undergo catastrophic collapse once nuclear fuel is exhausted, igniting a supernova event. This explosive release of energy would outshine entire galaxies temporarily, unleashing intense radiation, shock waves, and expelled stellar material into space. The immediate vicinity of UY Scuti would be subjected to a barrage of high-energy photons and particles, stripping away any remaining layers of the star's outer envelope at velocities reaching thousands of kilometers per second. This process would seed the surrounding interstellar medium with heavy elements synthesized during the star's life and the supernova itself. Elements such as iron, nickel, and other metals would enrich nearby molecular clouds, fostering the conditions necessary for future star formation. The shock waves from the explosion could compress nearby gas clouds, triggering the gravitational collapse that sparks new generations of stars, thus playing a crucial role in galactic chemical evolution and stellar demographics. However, the explosion's impact would depend heavily on the local environment and the star's initial mass. For a star as colossal as UY Scuti, the supernova might leave behind a dense core, either a neutron star or, if the mass exceeds certain limits, a black hole. The supernova remnant would expand outward, gradually dispersing into the galaxy. In the process, the intense radiative and kinetic energy released could potentially disrupt existing planetary systems or star-forming regions within a few parsecs, although the precise effects would diminish with distance. While the explosion marks the star's death, it also acts as a catalyst for cosmic renewal. The dispersal of heavy elements and the energetic shock waves shape the interstellar landscape, influencing subsequent star and planet formation. Understanding these explosive processes, particularly in such massive stars, reveals insights into the life cycles of galaxies and the cosmic distribution of elements, highlighting the interconnectedness of stellar death and creation. Studying the ultimate fate of UY Scuti extends beyond understanding a solitary star. It offers vital insights into the broader mechanisms governing stellar evolution and the life cycle of massive celestial bodies. As a red supergiant nearing the end of its life, UY Scuti exemplifies the processes that shape some of the universe's most spectacular and influential phenomena. Observing its mass loss, pulsations, and eventual transition into a supernova enriches our comprehension of how such colossal stars contribute to cosmic recycling. When UY Scuti sheds its outer layers, it disperses enriched materials into space, seeding future generations of stars and planets. This cycle of matter redistribution plays a key role in galactic evolution, influencing star formation rates and the chemical composition of the interstellar medium. Understanding the star's demise also informs models of supernova mechanisms, which are critical for interpreting the origins of heavy elements and the formation of compact remnants like neutron stars or black holes. Since UY Scuti's mass is immense, its supernova could produce a black hole, offering clues about the thresholds and conditions that determine whether a collapsing star leaves behind a neutron star or a black hole. These insights are essential for refining theoretical frameworks that describe extreme physics under intense gravity and high-energy processes. Moreover, tracking the evolution of stars like UY Scuti enhances our predictive capabilities regarding the life cycles of massive stars in various galactic environments. It helps astrophysicists calibrate models of stellar lifespan, mass loss rates, and the influence of metallicity, which vary across the universe. Consequently, understanding UY Scuti's fate not only illuminates the destiny of one of the largest stars known, but also aids in constructing a more comprehensive picture of stellar populations and their cumulative impact on galactic dynamics. Ultimately, UY Scuti's life and death serve as a cosmic laboratory, bridging the microcosm of stellar physics with the macrocosm of galaxy formation and evolution. Its story underscores the interconnectedness of celestial phenomena and the importance of studying extreme objects to grasp the grand architecture of the universe. UY Scuti's extraordinary scale acts as a crucial reference point in unraveling the vastness and complexity of the universe. By pushing the boundaries of our understanding of stellar dimensions, this supergiant star exemplifies the extremes to which stellar bodies can grow. Its immense size challenges astronomers to refine the methods of measuring celestial objects at such vast distances, inherently deepening our grasp of the universe's structure. The sheer magnitude of UY Scuti prompts a re-evaluation of how stars influence their surroundings. It exemplifies the upper limits of stellar evolution, illustrating how massive stars can expand to colossal sizes before ending their life cycles in supernova explosions or collapsing into neutron stars or black holes. These processes, driven in part by the size and mass of stars like UY Scuti, contribute to the recycling of material within galaxies, influencing subsequent generations of star formation. Furthermore, the luminosity and energy output of UY Scuti offer insights into the internal physics governing stellar stability and fusion processes at extreme scales. Studying such stars illuminates the relationship between a star's size, luminosity, and lifespan, which in turn helps define the distribution of stellar populations across different galactic environments. Understanding these parameters extends our comprehension of galaxy formation, revealing how massive stars act as cosmic engines, synthesizing heavy elements and dispersing them into the interstellar medium. The existence of stars like UY Scuti also provides a window into the early universe. Their formation and evolution echo conditions that prevailed in the universe's infancy, offering clues about the processes that shaped galaxies from primordial matter. In this way, UY Scuti helps paint a grander picture, one where the scale of individual stars mirrors the larger cosmic architecture, emphasizing the interconnectedness of stellar life cycles and galactic evolution. As we probe the limits of stellar size and luminosity, UY Scuti serves as a pivotal benchmark, anchoring our understanding of the universe's immense, intricate tapestry. Its study not only reveals the nature of stars, but also illuminates the grand cosmic web that binds galaxies together. Supergiant stars like UY Scuti occupy a pivotal role in shaping the evolutionary pathways of galaxies. Their immense mass and luminosity influence the surrounding interstellar environment, driving processes that have far-reaching consequences for galaxy formation. As some of the most luminous and voluminous stars, supergiants act as cosmic engines, injecting energy, enriching the interstellar medium with heavy elements, and shaping the conditions for subsequent generations of star formation. During their relatively brief yet tumultuous lives, these colossal stars undergo intense mass loss episodes through powerful stellar winds and eruptions. This shedding of material disperses enriched gas and dust into their environs, contributing to the galactic chemical evolution. The expelled matter seeds the birth of new stars and planetary systems, playing a crucial part in the ongoing cycle of matter recycling within galaxies. The composition of this material, enriched with elements forged in the star's core, influences the metallicity and diversity of future stellar populations. Furthermore, supergiants like UY Scuti help astronomers understand the upper limits of stellar mass and luminosity, informing models of stellar evolution and the initial mass function. Their violent endpoints, supernova explosions or direct collapse into black holes, serve as catalysts for galaxy dynamics, potentially triggering starburst activity or shaping galactic structures through shock waves. These cataclysmic events also serve as cosmic laboratories for studying extreme physics and nucleosynthesis. In addition, the distribution and frequency of supergiant stars within galaxies reflect the galaxy's star formation history and initial mass distribution. By analyzing populations of such luminous giants, astronomers gain insights into the evolutionary stages of different galactic environments, from spiral arms to irregular systems. Consequently, supergiants like UY Scuti are not only markers of stellar evolution, but also vital components in understanding the grand narrative of galaxy assembly and transformation across cosmic time. The study of UY Scuti extends beyond understanding a single extraordinary star. It significantly enhances our broader comprehension of stellar populations across the cosmos. As one of the largest known stars, UY Scuti exemplifies the upper limits of stellar size, luminosity, and mass, challenging our models of star formation and evolution. By analyzing its properties, astronomers gain insights into the processes that give rise to such behemoths, shedding light on the initial conditions and environmental factors conducive to the birth of massive stars. Investigations into UY Scuti's life cycle reveal the pathways massive stars follow, from their turbulent formation phases within dense molecular clouds to their eventual transformation into red supergiants. These pathways inform theories about the distribution and life cycle of similar stars in different galactic environments. Studying its mass loss, for instance, helps refine models of how such stars contribute to the enrichment of the interstellar medium with heavy elements, influencing subsequent generations of star formation. Furthermore, UY Scuti's extreme physical characteristics serve as benchmarks against which stellar models are tested and calibrated. Its luminosity and size push the boundaries of theoretical predictions, prompting refinements in our understanding of stellar physics, including fusion processes, opacity, and energy transport in supergiant atmospheres. Observations of its variability deepen our knowledge of pulsation mechanisms in massive stars, which can vary widely across stellar populations. Analyzing UY Scuti also illuminates the diversity within stellar populations, illustrating the range of possible stellar endpoints and the conditions leading to different evolutionary outcomes. Its existence hints at the frequency and distribution of such giants in the universe, informing statistical models of stellar demographics across galaxies. Ultimately, UY Scuti acts as an invaluable natural laboratory, bridging the gap between theoretical astrophysics and observable phenomena, thereby enriching our grasp of the complex tapestry of stellar life in the universe. UY Scuti stands as a natural laboratory for understanding the outermost boundaries of stellar physics, exemplifying the extremes that stars can attain in size, luminosity, and structural complexity. As a red supergiant, its immense radius pushes the limits of what is physically sustainable within a star's internal pressures and energy production mechanisms. Its vast surface area, spanning hundreds of millions of kilometers, challenges existing models of stellar stability, forcing astronomers to refine theories about how such colossal atmospheres can remain gravitationally bound despite intense radiation and mass loss. The star's extraordinary luminosity, which outshines many other giants by a significant margin, raises questions about the upper limits of stellar brightness. UY Scuti's intense output is a direct consequence of its extensive surface area and relatively cool temperature, illustrating how size and temperature interplay to produce extreme luminosities. This makes it an essential case study for understanding how stars can maintain such high energy outputs without dispersing their outer layers prematurely. Its variable brightness further complicates the picture, revealing complex pulsations and convective processes that occur at scales unseen in smaller stars. Structurally, UY Scuti demonstrates that stellar density diminishes drastically at these sizes, with its outer layers being tenuous and prone to episodic mass ejections. These phenomena offer insights into how stars shed mass at the end of their life cycles, influencing theories of stellar evolution and the formation of supernova remnants or neutron stars. The star's internal fusion processes, although similar to those in less massive stars, operate under extreme conditions that test the limits of nuclear physics under low-density, high-volume environments. In essence, UY Scuti embodies the parameters at which our understanding of stellar physics is tested and stretched to its boundaries. Its existence compels astrophysicists to reconsider the theoretical maximums of stellar size and brightness, parameters that are fundamental to models of star formation, evolution, and the ultimate fate of massive stars in the universe. The extraordinary dimensions of UY Scuti have prompted astronomers to reconsider the upper limits of stellar size and luminosity, challenging existing models of stellar physics. Traditionally, theories about the maximum size of stars have been constrained by the balance between gravitational forces and radiation pressure, as well as the stability of nuclear fusion processes within a star's core. UY Scuti's sheer scale pushes these boundaries, suggesting that stars might achieve sizes previously thought impossible, especially during their late evolutionary stages. Its immense radius implies that, under certain conditions, a star can expand far beyond the conventional thresholds, prompting refinements in models that account for the physical processes enabling such growth. Luminosity, closely tied to size and temperature, also comes under scrutiny when examining stars like UY Scuti. Its brightness, driven by the enormous surface area and ongoing fusion in its core, exceeds the expectations set by earlier models. This has led scientists to explore how stellar luminosity scales with size and whether previously assumed limits, such as the Eddington luminosity, which balances radiation pressure and gravity, can be surpassed or need to be redefined. The star's variability adds further complexity, revealing how pulsations, mass loss, and atmospheric dynamics influence luminosity at these extremes. These insights compel astrophysicists to develop more nuanced theories that encompass a broader range of stellar behaviors and structures. The case of UY Scuti underscores the importance of considering diverse evolutionary pathways and the role of environmental factors in shaping stellar limits. It suggests that the universe might harbor even larger and more luminous stars than those currently observed, especially in regions with unique conditions that favor rapid mass accumulation or inhibited mass loss. Consequently, UY Scuti serves as a natural laboratory for testing the bounds of stellar physics, prompting ongoing revisions to our understanding of how massive stars can become and how bright they can shine. This ongoing inquiry deepens our grasp of stellar evolution, revealing the universe's capacity for extremes and pushing the frontiers of cosmic knowledge. Supergiant stars like UY Scuti play a pivotal role in shaping the chemical landscape of the universe. Their significance extends beyond their staggering sizes and luminosities, delving into the very processes that forge and disperse the elements fundamental to planetary systems and life itself. During their evolved phases, these colossal stars undergo intense fusion reactions in their cores, synthesizing heavier elements such as carbon, oxygen, and even some heavier nuclei through successive fusion cycles. As they approach the end of their life cycles, their outer layers become unstable, leading to substantial mass loss via powerful stellar winds and episodic eruptions. This mass ejection enriches the surrounding interstellar medium with freshly forged elements, effectively recycling stellar material into the cosmos. These enriched clouds serve as the nurseries for new generations of stars and planets, embedding the universe with the chemical diversity necessary for complex chemistry and, ultimately, life. The heavy elements dispersed by supergiants like UY Scuti are crucial in forming rocky planets and enabling biological processes, making their contribution to cosmic chemical evolution paramount. Studying supergiant stars provides insights into the efficiency and mechanisms of nucleosynthesis, the process of creating new atomic nuclei within stellar interiors. Observations of their spectra reveal the abundance and distribution of elements, offering a window into the stellar core processes and the conditions under which these elements are produced. Additionally, the mass loss phenomena observed in supergiants help refine models of stellar evolution, shedding light on how stars shed their outer layers and transition into later evolutionary stages, such as supernovae or neutron stars. By understanding the life cycle of supergiants, scientists also gain context for the broader chemical evolution of galaxies. Since these stars are among the most luminous and long-lived stellar beacons, their study informs models of galaxy formation and evolution. In essence, supergiant stars act as cosmic alchemists, continuously transforming primordial material into the rich tapestry of elements that define our universe's complexity and diversity. While UY Scuti itself does not directly inform us about the universe's age or its rate of expansion, its observations play a crucial role in refining our broader cosmological understanding. Studying such colossal stars offers insights into the processes of stellar evolution, which are fundamental benchmarks for calibrating cosmic timelines. By understanding the life cycles of massive stars, astronomers can better estimate the rate at which galaxies evolve, providing indirect clues about the universe's age. Moreover, precise measurements of UY Scuti's distance and intrinsic properties contribute to the calibration of distance scales that underpin our comprehension of cosmic expansion. For instance, establishing accurate luminosities and distances to nearby stellar objects helps refine standard candles like Cepheid variables and Type Ia supernovae, which serve as fundamental tools for measuring vast cosmic distances. These measurements, in turn, influence the calculations of the universe's expansion rate, known as the Hubble constant. Advancements in observing the extremities of stellar sizes, exemplified by UY Scuti, also enhance our understanding of the universe's early conditions. The formation of such massive stars in different epochs offers clues about the density and composition of the primordial universe, indirectly informing models of cosmic evolution. By studying the properties and distribution of large stars across different galaxies, scientists can piece together the timeline of galaxy formation and growth, which are intimately connected to the universe's age. Furthermore, the challenges encountered in observing UY Scuti, such as its distance and the surrounding dust, drive technological innovations in telescopic and data analysis techniques. These improvements bolster our capacity to observe distant galaxies and cosmic phenomena that are crucial to understanding universe expansion. As a result, detailed studies of stars like UY Scuti help refine the parameters that define our cosmological models, bridging the gap between stellar astrophysics and the grand scale of universal evolution. Studying colossal stars like UY Scuti offers profound insights into the universe's expansive scale and the underlying principles that govern stellar evolution. Their immense size acts as a cosmic yardstick, stretching our understanding of how matter can organize itself under extreme conditions. By examining the properties of such giants, astronomers gain a clearer perspective of the vastness of the cosmos, as well as the processes that lead to the formation of the most massive stellar bodies. These stars serve as natural laboratories, allowing scientists to observe phenomena such as nuclear fusion at different stages and the complex interactions within their extended atmospheres. The sheer scale of these stars underscores the diversity within the universe. While the Sun exemplifies a stable middle-aged star, giants like UY Scuti reveal the dramatic extremes of stellar life cycles. Studying their internal structures and surface behaviors helps refine models of stellar physics, clarifying how massive stars evolve, shed their outer layers, and ultimately end their lives, sometimes in spectacular supernovae or collapsing into black holes. These processes influence galaxy evolution, enriching the interstellar medium with heavy elements essential for planet formation and life. Furthermore, the challenges involved in measuring such enormous objects push technological and methodological boundaries, fostering advancements in telescopic resolution, data analysis, and interstellar distance calculations. These innovations ripple outward, enhancing our capacity to explore more distant and faint objects across the universe. The lessons learned from UY Scuti and similar stars extend beyond pure astrophysics. They deepen our appreciation of the universe's scale, illustrating how seemingly incomprehensible distances and sizes are subject to human curiosity and scientific inquiry. Ultimately, studying the largest stars emphasizes the universe's vast complexity and interconnectedness. It reminds us that our cosmic neighborhood is just a tiny fragment within an incomprehensibly large expanse, an inspiring testament to the grandeur of the universe and the endless pursuit of understanding that drives scientific exploration. This perspective fosters humility, curiosity, and a renewed sense of wonder about our place in the cosmos. UY Scuti's extraordinary scale and luminous presence have fueled curiosity and admiration across both scientific communities and the general public. Its sheer size, far surpassing typical stellar dimensions, evokes a sense of wonder, prompting questions about the universe's limits and the nature of stellar giants. For scientists, UY Scuti offers a natural laboratory to test and refine models of stellar physics, especially concerning the late stages of massive star evolution. Its extreme properties push the boundaries of current understanding, challenging assumptions about mass loss, stability, and the physical processes governing supergiant stars. Meanwhile, the star's captivating size and brightness have cemented its place in popular imagination. Media outlets often portray UY Scuti as a cosmic behemoth, emphasizing its capacity to swallow our solar system whole, a vivid metaphor that sparks awe and curiosity. These vivid descriptions make complex astrophysical concepts accessible, inspiring a sense of scale that is difficult to grasp otherwise. The story of such a colossal star resonates with audiences because it embodies the universe's grandeur and mystery, fueling fascination with the cosmos. Educational efforts frequently highlight UY Scuti as an illustrative example of stellar extremes. Its dramatic size and luminosity serve as compelling visuals in classrooms, documentaries, and planetarium shows, helping students and viewers grasp the vastness of space and the diversity of stellar life cycles. This star becomes a symbol of the universe's diversity, an anchor point for discussions about the life cycle of massive stars and the dynamic processes shaping galaxies. Public fascination with UY Scuti also stems from its role in inspiring curiosity about our place in the cosmos. As an awe-inspiring object, it prompts questions about the universe's scale, the life cycle of stars, and the potential for other colossal objects lurking in the depths of space. This blend of scientific intrigue and poetic grandeur ensures that UY Scuti remains a captivating figure in both scholarly research and popular culture, bridging the gap between complex astrophysics and human wonder. UY Scuti's extraordinary characteristics have captured the imagination far beyond the scientific community, embedding itself into popular culture, media, and educational narratives. Its immense size and luminous nature serve as a powerful symbol of the universe's grandeur, inspiring a blend of awe and curiosity among the general public. Documentaries, science programs, and space-themed entertainment frequently showcase UY Scuti when illustrating the sheer scale of celestial objects, often using vivid visualizations and animations to help viewers grasp concepts that are otherwise difficult to conceive. In media portrayals, UY Scuti often appears as a focal point for stories about the universe's mysteries, fueling speculative discussions about the boundaries of stellar evolution and the potential for discovering even larger stars. Its image and name are woven into art, literature, and digital platforms that aim to ignite interest in astronomy, making complex concepts accessible and engaging. This widespread representation helps demystify the cosmos, transforming abstract scientific data into compelling narratives that resonate with audiences of all ages. Educational initiatives leverage UY Scuti's prominence to inspire curiosity and motivate learning. Astronomy textbooks, planetarium shows, and science outreach programs frequently feature UY Scuti as a prime example of the universe's extremes. Its story exemplifies the importance of technological innovation, such as advanced telescopes and measurement techniques, in expanding our cosmic understanding. Interactive tools and virtual reality experiences often depict UY Scuti's scale, allowing students and enthusiasts to explore its dimensions firsthand, thereby fostering a deeper appreciation of stellar phenomena. Beyond its scientific importance, UY Scuti has become a symbol of human curiosity and the quest for knowledge. Its prominence in popular culture and education underscores the universal desire to explore the unknown. By transforming complex astrophysical concepts into captivating stories and visualizations, UY Scuti continues to serve as a bridge between scientific discovery and public imagination, inspiring future generations to look beyond our world and pursue the mysteries of the universe with passion and determination. The awe-inspiring scale of UY Scuti serves as a powerful catalyst for inspiring the next generation of astronomers and astrophysicists. Its sheer size and luminous complexity ignite curiosity about the universe's most extreme phenomena, encouraging students and researchers alike to push the boundaries of scientific understanding. The star's enigmatic nature underscores the importance of advanced observational techniques, fostering innovation in telescope technology, data analysis, and modeling approaches. Aspiring scientists are motivated to develop new methods to measure and interpret the properties of distant celestial objects, often leading to breakthroughs that extend well beyond the study of a single star. Educational programs frequently leverage UY Scuti as a prime example of the universe's grandeur and the ongoing quest to comprehend stellar evolution. Its mysteries challenge students to think critically about the physical laws governing stars, inspiring careers dedicated to unraveling cosmic secrets. Additionally, the star's role in expanding our knowledge of stellar life cycles reinforces the importance of interdisciplinary collaboration, combining physics, chemistry, and computational science to decode the complexities of massive stars. This multidisciplinary approach cultivates a new generation of scientists equipped to tackle future astronomical challenges. The star also functions as a compelling case study, illustrating the importance of international cooperation and technological advancement in astronomy. As projects aimed at understanding objects like UY Scuti grow more ambitious, they often require substantial funding and resource allocation. Consequently, the star's prominence in scientific discourse influences funding agencies and policymakers to prioritize large-scale observational projects, space telescopes, and computational infrastructure. The allure of such extraordinary objects captures the public imagination, fostering increased support and investment in fundamental research. Ultimately, UY Scuti's grandeur acts as both a symbol and a catalyst, encouraging youth to pursue careers in science and guiding institutional priorities toward exploring the universe's most profound mysteries. Its presence in scientific inquiry exemplifies the enduring human drive to comprehend the cosmos, inspiring a continual cycle of discovery and innovation that shapes the future of astronomical research. The awe-inspiring scale of UY Scuti compels scientific communities and funding agencies to reconsider their priorities and approaches to astrophysical research. As the largest known star, UY Scuti pushes the boundaries of current models of stellar physics, prompting renewed investment in high-precision observational technologies and theoretical simulations. The star serves as a natural laboratory for testing the limits of our understanding of stellar formation, evolution, and mass loss mechanisms. Consequently, research initiatives that can provide more detailed data, such as advanced telescopes, interferometry, and space-based observatories, become increasingly vital. This pursuit of knowledge often influences funding strategies by emphasizing projects that promise to resolve fundamental questions about the life cycles of massive stars. The sheer scale of UY Scuti underscores the importance of exploring extreme astrophysical environments, leading to prioritization of large-scale international collaborations and the development of next-generation instruments. These investments are justified not only by the quest to understand such colossal objects, but also by their broader implications for galaxy formation, chemical enrichment, and the cosmic life cycle. Furthermore, the existence of stars like UY Scuti fosters a reassessment of the boundaries of stellar physics, encouraging interdisciplinary research that combines astrophysics, computational modeling, and even particle physics. The challenge of accurately simulating such extreme phenomena necessitates substantial funding, shaping research agendas toward high-performance computing and innovative observational methodologies. Yet, the star's enormity also raises questions about resource allocation and the societal value of astronomical research. As budgets are finite, decision-makers must weigh the importance of studying objects like UY Scuti against other scientific and practical priorities. Nonetheless, the fascination and curiosity sparked by such celestial giants often galvanize public interest and political support, ultimately influencing the allocation of research funds. The study of UY Scuti exemplifies how extraordinary cosmic objects can serve as catalysts for scientific advancement and strategic investment, emphasizing the ongoing dialogue between curiosity-driven exploration and pragmatic resource management in the pursuit of cosmic understanding. The staggering scale of stars like UY Scuti prompts profound ethical and philosophical reflections on humanity's place in the universe. Confronted with objects so immense that they dwarf entire planetary systems, we are compelled to consider the implications of our pursuit of cosmic knowledge. This pursuit often raises questions about our responsibilities as explorers of the universe. For instance, as our observational technologies advance, enabling us to peer deeper and more precisely into the cosmos, we must grapple with the consequences of our discoveries, both scientifically and ethically. Could understanding such colossal stars influence our perspective on planetary stewardship, environmental conservation, or our own survival? While stars like UY Scuti are distant and seemingly disconnected from earthly concerns, their awe-inspiring scale underscores the fragility and uniqueness of our own planet, prompting a sense of stewardship rooted in humility. Philosophically, the existence of such titanic celestial bodies challenges notions of scale, significance, and human centrality. In the face of these cosmic giants, human life appears transient and minuscule. Yet this recognition can inspire a profound appreciation for our pursuit of knowledge. It invites us to contemplate existential questions about the universe's origin, purpose, and ultimate fate. Does the vastness of stars like UY Scuti diminish human importance, or does it elevate our curiosity and drive to understand the cosmos? These questions underscore the importance of scientific inquiry, not just as a quest for facts, but as a reflection of humanity's innate desire to find meaning amid the infinite. Furthermore, the study of such stars fosters a sense of collective responsibility. As we expand our understanding of stellar phenomena, we are reminded of the interconnectedness of all cosmic entities and the importance of safeguarding our own planetary environment. Ultimately, exploring the universe's grandest features deepens our philosophical understanding of existence, challenging us to reconcile our insignificance with our relentless pursuit of knowledge and purpose. Communicating the grandeur of UY Scuti to a general audience exemplifies humanity's enduring desire to comprehend the universe, yet it also highlights the inherent challenges of translating such cosmic scale into accessible understanding. The star's immense size and luminosity often defy everyday experience, making it difficult for non-specialists to grasp the true magnitude of its existence. When describing a celestial object that could swallow our entire solar system, the task is to bridge the gap between abstract scientific data and intuitive perception. One significant obstacle lies in the abstract nature of astronomical measurements. Terms like radius, luminosity, and distance are mathematically precise but lack immediate visual impact. Conveying what it truly means for UY Scuti to be thousands of times larger than our Sun requires creative analogies that resonate emotionally without oversimplifying the science. For example, comparing its size to familiar objects or scale models can help, but these comparisons must be carefully calibrated to avoid distortions or misconceptions. Another challenge involves overcoming the emotional and cognitive barriers associated with comprehending vast cosmic distances and sizes. The public's intuition about scale is limited. Humans naturally relate to familiar sizes and distances, yet stars like UY Scuti operate on a scale that stretches the imagination. Explaining the methods used to measure such distant objects, like parallax, brightness analysis, and spectral data, can be technical and intimidating, further complicating effective communication. Additionally, there is the risk of sensationalism, which can lead to misconceptions or exaggerated perceptions of the star's significance. Balancing awe-inspiring descriptions with scientific accuracy demands careful storytelling that emphasizes the star's role in advancing astrophysics rather than merely its size. Ultimately, the challenge of conveying UY Scuti's significance lies in translating complex scientific truths into compelling narratives that evoke curiosity and wonder. Doing so requires not only clarity and creativity, but also a nuanced understanding of how humans perceive scale and significance within the vast, intricate cosmos. Conveying the grandeur and scientific importance of UY Scuti to a broad audience presents unique challenges rooted in both its scale and the abstract nature of stellar phenomena. One significant obstacle lies in translating the star's extraordinary dimensions into relatable concepts. While comparisons to our solar system help, they often fail to capture the true magnitude, leaving audiences with a sense of awe that can be difficult to grasp fully. Explaining that UY Scuti's radius could encompass thousands of times the Sun's size risks sounding like mere numbers rather than evoking the profound implications of such scale. Another challenge stems from the abstract nature of stellar physics itself. Concepts like luminosity, mass loss, and fusion processes are inherently complex, requiring simplified analogies that may inadvertently distort or oversimplify scientific accuracy. Striking a balance between accessibility and precision demands careful storytelling, ensuring that audiences are inspired without being overwhelmed by technical minutiae. Furthermore, the star's distance and the limitations of current observational techniques complicate efforts to portray its true nature vividly. When most people cannot directly observe UY Scuti, reliance on images and models, while invaluable, can sometimes foster misconceptions about the star's appearance and properties. Explaining how interstellar dust and measurement uncertainties influence our understanding becomes essential, but can further obscure the star's real essence. Cultural and emotional barriers also influence communication. Conveying the significance of such an astronomical titan in a way that resonates emotionally requires bridging scientific facts with human curiosity and wonder. This involves crafting narratives that evoke a sense of exploration and the universe's vastness, encouraging audiences to see themselves as part of a larger cosmic story. As science advances, new discoveries about UY Scuti could challenge existing perceptions, making it crucial to adapt our explanations continually. The task is not merely to inform, but to inspire curiosity and humility, acknowledging that even our most detailed knowledge is but a glimpse into the universe's grand tapestry. Future discoveries about UY Scuti hold the potential to profoundly influence our comprehension of stellar physics, cosmic scales, and the universe's grand architecture. As observational technology advances, through more powerful telescopes, interferometry, and perhaps even space-based observatories, Scientists anticipate uncovering subtle details about this colossal star's internal processes, atmosphere, and surrounding environment. Such insights could challenge existing models of how stars form, evolve, and shed mass, especially in the extreme conditions characteristic of hypergiance. Precise measurements might reveal variations in its size, luminosity, or surface phenomena, prompting revisions of stellar evolution theories and refining our understanding of the late stages of massive stars. Unraveling the mysteries of UY Scuti may also impact our perception of galactic dynamics. As a luminous and massive object, it influences its local environment through intense radiation and stellar winds, which shape nearby interstellar matter and potentially trigger star formation. New data could illuminate the feedback mechanisms between massive stars and their surroundings, emphasizing their role in the broader galactic ecosystem. Furthermore, understanding the precise mechanisms behind UY Scuti's mass loss and variability could shed light on how such giants enrich the interstellar medium with heavier elements, ultimately contributing to the chemical evolution of galaxies. On a philosophical level, each incremental discovery about UY Scuti pushes the boundaries of our cosmic perspective. It emphasizes the staggering diversity of stellar phenomena and underscores the vastness of the universe, reminding us that our solar system is but a tiny speck within a universe filled with wonders beyond current imagination. As we refine our knowledge about stars like UY Scuti, we deepen our appreciation for the complexity and grandeur of the cosmos, fostering a sense of curiosity and humility about our place within it. These ongoing revelations serve as a testament to humanity's relentless pursuit of understanding, continually expanding the horizon of what we consider possible in the universe's vast expanse. UY Scuti stands as a luminous testament to the astonishing diversity and scale of stellar phenomena in our universe. Its immense size not only captures scientific curiosity, but also challenges our understanding of stellar physics, pushing the boundaries of current models. As one of the largest known stars, UY Scuti's volume is so vast that it could theoretically engulf our entire solar system, a fact that underscores the extraordinary extremes that stars can reach. This immense scale invites questions about how such colossal structures form, sustain themselves, and evolve over cosmic timescales. The significance of UY Scuti extends beyond mere size. It offers a rare natural laboratory for studying the limits of stellar stability, mass loss, and energy output. Its luminosity, driven by an enormous surface area, illuminates how stars can radiate vast amounts of energy despite relatively cool surface temperatures typical of red supergiants. Observing and modeling these characteristics provide crucial insights into the life cycles of the most massive stars and their influence on their galactic environments. The star's role in enriching the cosmos with heavy elements through stellar winds and eventual supernova explosions further emphasizes its importance in cosmic evolution. Moreover, UY Scuti exemplifies the dynamic and often unpredictable nature of stellar life. Its variability in brightness, linked to pulsations and atmospheric changes, reflects the complex interplay of internal fusion processes and outer layer dynamics. These processes, occurring on scales difficult to grasp, highlight the delicate balance of forces that sustain such enormous stars and ultimately lead to their dramatic demise. By studying UY Scuti, astronomers gain invaluable clues about the upper limits of stellar mass and size, informing theories about the formation of black holes and neutron stars. In essence, UY Scuti embodies the extremes of stellar physics and cosmic scale. Its existence challenges our notions of what stars can be, serving as a beacon of scientific inquiry into the universe's most majestic and mysterious objects. As technology advances, our understanding of this colossal star will deepen, revealing even more about the universe's capacity for grandeur and complexity. UY Scuti stands as a testament to the extraordinary extremes that stellar physics can reach, pushing the boundaries of our understanding of how stars form, evolve, and interact with their cosmic environment. Its immense size and luminosity serve as natural laboratories, revealing the limits of current astrophysical models. For instance, The star's vast outer envelope demonstrates how matter can be distributed over such enormous scales that traditional concepts of stellar density and internal pressure are challenged. The low density of its outer layers, despite the star's colossal volume, highlights the delicate balance between gravity and radiation pressure at such extremes, offering insights into the physics governing mass loss and stellar winds. The star's variability and the complex processes driving its evolution exemplify how stars can exist in transient, unstable phases that defy simplified models. UY Scuti's significant mass loss during its red supergiant phase illustrates the interconnectedness of stellar life cycle stages and how they influence galactic ecosystems, enriching the interstellar medium with heavy elements essential for planet formation and life. Its atmosphere, rich in molecules and dust, demonstrates how stellar environments at these scales are dynamic and chemically complex, providing clues about the processes that shape star death and rebirth. Studying UY Scuti also exposes the limitations of our observational technologies, prompting innovations in telescope design, data calibration, and analytical techniques. The star's sheer scale and faint surface temperature push the boundaries of spectral analysis, requiring increasingly sophisticated models to interpret observational data accurately. Its extreme properties serve as a benchmark for testing theories of stellar physics under conditions unattainable in terrestrial laboratories, emphasizing the importance of integrating observational data with advanced computational simulations. In essence, UY Scuti exemplifies the cosmos's capacity for extremes, revealing that stars are not merely luminous spheres, but dynamic entities operating at the very edges of physical laws. Its study underscores the universe's inherent complexity, reminding us that even the most luminous and massive objects are governed by subtle, intricate processes that challenge our understanding and inspire continued exploration. Studying the colossal nature of stars like UY Scuti reveals much about the universe's intricate and often surprising complexity. These stars serve as natural laboratories for testing the boundaries of astrophysical theories. For instance, their immense sizes and entities push scientists to refine models of stellar structure, particularly in understanding how energy transfer occurs within such vast, diffuse atmospheres. When astronomers observe how UY Scuti loses mass through powerful stellar winds, it provides insights into the life cycles of massive stars and the mechanisms driving their eventual transformation into supernovae or neutron stars. These processes are not merely isolated phenomena, but are interconnected with the broader cosmic environment, influencing the chemical enrichment of galaxies. The challenges faced in studying such giants also highlight the importance of technological innovation. Pushing observational limits to measure their properties encourages the development of more sensitive telescopes and advanced data analysis techniques. This relentless pursuit of knowledge underscores a fundamental lesson. The universe is far more dynamic and complex than initial models suggest. Each discovery about stars like UY Scuti prompts scientists to revisit and refine their understanding of fundamental physics, from nuclear fusion to gravitational interactions on a galactic scale. Furthermore, the existence of these extraordinary stars underscores the diversity and adaptability inherent in cosmic evolution. Their extreme characteristics remind us that the universe is not a uniform arena, but a tapestry woven with objects that challenge our assumptions and inspire new hypotheses. While their size and brightness seem almost beyond comprehension, these stars serve as a testament to nature's capacity for producing phenomena that stretch the limits of human curiosity and scientific inquiry. By studying UY Scuti and its peers, scientists gain a deeper appreciation of the universe's layered complexity. These giants exemplify how vast scales, energetic processes, and cosmic timescales intertwine, fueling ongoing exploration. Each new observation and theoretical development not only enhances our understanding of individual stars, but also illuminates overarching principles that govern the universe's intricate and awe-inspiring fabric. The study of UY Scuti continues to ignite scientific curiosity by pushing the boundaries of observational astronomy and theoretical modeling, prompting researchers to develop innovative techniques to decipher the complexities of such colossal stars. Its extreme size and luminosity serve as natural laboratories for testing the limits of stellar physics, challenging existing models and inspiring new hypotheses about the processes governing massive star evolution. For instance, understanding how UY Scuti sustains its stability despite its enormous scale encourages scientists to refine theories related to energy transport, convection, and mass loss in red supergiants. These insights have broader implications as they influence how astronomers interpret the life cycle of similar stars across the galaxy. The quest to measure UY Scuti's properties accurately also drives technological advancements. Enhanced telescopic instruments, adaptive optics, and space-based observatories aim to resolve the star's surface features and atmospheric dynamics with increasing precision. Such detailed observations reveal surface irregularities, pulsation patterns, and mass ejection events that are crucial for understanding how massive stars shed material and evolve toward their final stages. These phenomena are not only vital for astrophysics, but also inform models of chemical enrichment in galaxies. As mass loss from stars like UY Scuti disperses heavy elements into the interstellar medium. Moreover, studying UY Scuti sparks curiosity about the broader cosmic environment. Its sheer scale and luminosity influence our understanding of the feedback mechanisms that regulate star formation in nearby regions. As scientists simulate the star's evolution, they gain insights into how massive stars impact their galactic neighborhoods, shaping the architecture and chemical composition of galaxies over cosmic timescales. The star's existence also prompts reflection on the limits of stellar mass and the initial conditions necessary for such giants to form, questions that deepen our comprehension of stellar and galactic genesis. Through these endeavors, UY Scuti becomes more than a distant, enigmatic object. It transforms into a catalyst for exploration, inspiring a continuous quest to unravel the fundamental processes that govern the universe's most magnificent structures. Ongoing research into UY Scuti not only deepens our grasp of the life cycles of the most massive stars, but also offers critical insights into the broader mechanisms governing stellar and galactic evolution. By refining models of how supergiants form, evolve, and ultimately shed their outer layers, scientists can better understand the complex interplay between stellar mass, luminosity, and lifespan. UY Scuti's extraordinary size and luminosity challenge existing theories, prompting revisions that incorporate more nuanced treatments of mass loss, convection, and energy transport in extreme stellar environments. As advanced observational techniques, such as interferometry and adaptive optics, continue to yield more precise measurements, models become increasingly accurate, revealing how such giants influence their surroundings through intense stellar winds and supernova precursors. These investigations also illuminate the role of supergiants like UY Scuti in enriching the interstellar medium with heavy elements. The mass loss processes observed in UY Scuti, for instance, contribute to the cycle of matter that fuels future star formation. This cyclical exchange impacts galactic chemical evolution, helping to shape the composition of subsequent stellar generations. Furthermore, understanding the mechanisms behind the dramatic expansion and contraction phases of stars like UY Scuti informs our comprehension of the end stages of massive stars, including supernovae and neutron star formation. Such events are vital for understanding the distribution of compact objects and the dynamics of galactic feedback. Research into UY Scuti also serves as a testing ground for the limits of stellar physics, pushing the boundaries of models that describe the most luminous and voluminous stars. As we uncover more about how these giants influence their host galaxies, the implications extend to cosmology, particularly in constraining the life cycle of matter in the universe and the formation of large-scale structures. Consequently, studying UY Scuti acts as a catalyst for broader astrophysical theories, linking the microcosm of stellar interiors to the macrocosm of cosmic evolution. Understanding stars like UY Scuti extends far beyond the realm of individual stellar curiosity. It fundamentally shapes our grasp of the universe's grand architecture. These colossal stars serve as natural laboratories for testing the limits of physical laws under extreme conditions. By studying their internal dynamics, fusion processes, and mass loss mechanisms, scientists gain insights into the fundamental principles governing matter at high energies, which can refine our understanding of physics itself. The enormous scale and luminosity of stars like UY Scuti also influence models of galaxy formation and evolution. Their intense radiation and stellar winds contribute to the enrichment of the interstellar medium with heavy elements, seeding future generations of stars and planetary systems. Recognizing the life cycle of such giants informs simulations of galactic ecology, illustrating how massive stars shape cosmic structures over millions of years. Moreover, these stellar behemoths challenge current technological capabilities, pushing the boundaries of observational astronomy. Efforts to resolve their properties demand innovations in telescope design, adaptive optics, and data analysis techniques. As we improve our ability to measure distant, massive stars amid interstellar dust, we develop new tools and methodologies that benefit broader astronomical research, including exoplanet detection and cosmic background studies. On a conceptual level, understanding the extremes exemplified by UY Scuti prompts us to refine cosmological models, including the parameters defining stellar populations, star formation rates, and the ultimate fate of massive stars. These insights can influence our comprehension of the universe's age, its expansion, and the distribution of matter on the largest scales. Finally, the quest to decode the secrets of stars like UY Scuti embodies humanity's innate drive to explore and understand the cosmos. As we unravel their mysteries, we not only expand scientific knowledge, but also inspire technological innovation and collaborative efforts across disciplines. This pursuit underscores the profound interconnectedness of astrophysics, engineering, and fundamental physics, igniting future endeavors to probe the universe's deepest enigmas. The story of UY Scuti exemplifies how confronting the universe's vastness can inspire a relentless pursuit of knowledge, fueling both scientific curiosity and technological innovation. Its extraordinary scale pushes astronomers to develop more sophisticated instruments capable of peering deeper into space, refining measurement techniques to reduce uncertainties, and overcoming the limitations imposed by Earth's atmosphere. The challenge of accurately gauging UY Scuti's size and luminosity, for instance, has driven advancements in interferometry and adaptive optics, which now enable astronomers to resolve objects with unprecedented precision despite their immense distances and the obscuring effects of interstellar dust. This pursuit of understanding encourages a broader view. It fosters interdisciplinary collaboration across fields such as physics, engineering, computer science, and data analysis. Efforts to model the star's complex behaviors, like its mass loss and variability, have necessitated the integration of computational simulations and high-powered processing, leading to innovations that benefit other areas of astrophysics and beyond. Each technological breakthrough, whether in detector sensitivity or data processing algorithms, not only advances stellar research, but also finds applications in fields like medical imaging, remote sensing, and quantum computing. Furthermore, the enigma of UY Scuti's immense size and luminous output challenges existing theories of stellar physics, prompting scientists to revisit and refine models of stellar evolution. This continual cycle of questioning and discovery exemplifies the scientific method's power, motivating future generations to seek answers about the universe's most extreme objects. As research pushes the boundaries of what is observable, it also underscores humanity's innate desire to understand our place among the stars. Ultimately, UY Scuti serves as a catalyst for technological progress and a symbol of our unyielding curiosity. Its story encourages scientists and engineers to innovate boldly, knowing that each discovery expands not only our cosmic understanding but also the technological capabilities that can transform multiple facets of human life. The star's grandeur becomes a mirror reflecting our collective aspiration to explore, comprehend, and transcend the limitations of current knowledge. UY Scuti stands as a profound emblem of the universe's boundless scale and complexity, embodying the awe-inspiring magnitude of cosmic phenomena that stretch human imagination and scientific understanding alike. Its immense size and luminosity serve not only as a testament to the extraordinary diversity of stellar life, but also as a symbol of our relentless pursuit to comprehend the universe's grandeur. In a broader sense, UY Scuti encapsulates humanity's innate curiosity about the cosmos, challenging our perceptions, pushing technological boundaries, and inspiring scientific innovation. As a beacon of cosmic scale, UY Scuti ignites a sense of wonder that transcends scientific inquiry, fostering cultural and philosophical reflections on our place within an incomprehensibly vast universe. Its existence prompts questions about the life cycles of stars, the processes that shape galaxies, and the ultimate fate of celestial bodies. This curiosity fuels ongoing research, driving advancements in observational technology and theoretical modeling. Each discovery about UY Scuti not only refines our understanding of stellar physics, but also deepens our appreciation for the interconnectedness of cosmic phenomena. Furthermore, UY Scuti's imposing presence acts as a symbol of the universe's unpredictable and dynamic nature. Its variability and complex atmospheric processes exemplify the intricate mechanisms at play in stellar evolution, reminding us that even the most massive stars are subject to change and transformation. This realization fosters humility and a sense of shared human endeavor, highlighting how collective effort, ingenuity, and technological progress have enabled us to glimpse into the life of a star so distant and colossal. Ultimately, UY Scuti embodies the spirit of exploration and discovery that defines astronomy. It stands as a monument to human curiosity, inspiring future generations to look beyond the known, to question, and to seek answers amid the stars. Its grandeur not only expands our scientific horizons, but also elevates our collective imagination, reminding us of the universe's infinite wonders waiting to be explored.